Good evening and welcome to the Sleepy Scientist. If you're here, it probably means the world has finally slowed down enough for you to listen to something quiet, something thoughtful. So take a breath, loosen your shoulders, and let the day drift away behind you. Tonight's journey is about time, that invisible thread that weaves together every moment you've ever known. It stretches from the first light of the universe to the gentle rhythm of your own heartbeat, marking the passage of everything that changes and everything that endures. Before we begin, I'd love to know where you're watching from. It's always fascinating to see how far these calm little stories travel, from cities that never sleep to the quietest corners of the countryside. And if you're new here, please consider giving the video a like and subscribing to the Sleepy Scientist. It really helps the channel find other curious minds who enjoy drifting through science at their own pace. And for those of you already subscribed, thank you truly. You're the heartbeat of this little corner of calm curiosity. Don't forget to tap the notification bell so you won't miss the next late-night voyage through the universe. I do hope this video doesn't keep you too awake, but if it does, at least you'll wake up knowing a little more about how time itself works. So settle in, let the seconds soften around you, and ask yourself, what is time, really? Time, it feels so ordinary. The steady tick between moments, the quiet rhythm of cause and effect. Yet beneath that calm surface lies one of the most profound mysteries in all of physics. For centuries we've measured time by the motion of things, the swing of a pendulum, the rise of the sun, the vibration of atoms. We've built machines that slice it into smaller and smaller pieces, hours, minutes, seconds, until we could measure a billionth of a heartbeat. But what exactly are we measuring? Is time something that flows, or something we simply notice? In everyday life, time feels like a gentle river carrying us forward. But to a physicist, it's not a current at all. It's a dimension, woven together with space into the fabric of space-time. A world where clocks disagree depending on how fast they move or how close they sit to a planet's gravity. This difference between how we feel time and how it behaves is what makes it so endlessly fascinating. The time you live through isn't the same as the time a satellite experiences, or the time deep inside a black hole, and yet somehow the universe keeps perfect order, a cosmic choreography of seconds, stretched and compressed, but never truly lost. In this calm journey, we'll wander from the heartbeat of atomic clocks to the farthest reaches of cosmic history. We'll follow the arrow of time that makes the past fixed and the future open, and we'll peek into the strange quantum realm where time might not exist at all. No equations, no rush, just the slow unfolding of one of the deepest questions we can ask. So as you settle deeper into rest, let your mind drift gently into the mystery. What if time isn't something we move through, but something that moves through us? Timekeeping began with shadows. Long before there were clocks or calendars, people simply watched the light move across the ground and learned that the world itself was a kind of clock. Sunrise and sunset marked the day. The changing stars divided the seasons. It was rough and imprecise, but it was enough to plant the first seeds of human rhythm. Life moved with the sky. The first real instruments of time were sundials, simple sticks and carved stones that turned sunlight into geometry. But sundials had a problem. They slept when the sun did. So humanity sought steadier rhythms, something that could tick even through the night. Water clocks came next, tripping patiently through narrow channels, followed by the hourglass, where the steady fall of sand gave minutes a tangible weight. Still, none of these were truly precise. They drifted and lagged, carried by weather and humidity, as if time itself refused to be tamed. Then came the pendulum. In the 1600s, Galileo noticed that a swinging lamp in a cathedral seemed to keep perfect rhythm, no matter how wide the swing. That tiny discovery led to clocks that could measure minutes and seconds with unprecedented accuracy. For the first time, humans began slicing time into smaller and smaller pieces, moments so brief they had once seemed invisible. The pendulum became the heartbeat of the world, ringing in churches, town halls, and observatories across continents. But physics doesn't sit still for long. Pendulums were replaced by springs and gears, and by the 1900s quartz crystals took over, vibrating tens of thousands of times per second when electric current passed through them. The ticking of gears became the humming of atoms, a shift from mechanics to physics itself. Quartz watches were marvels of consistency, tiny, portable, and accurate to within seconds per year. But even that wasn't enough. Humanity wanted perfection, and perfection demanded something smaller, something deeper, the oscillations of matter itself. Enter the atomic clock. Inside a quiet laboratory, scientists learned that atoms could keep time far more faithfully than any pendulum or crystal ever could. The hero of this story is the cesium-133 atom. When it switches between two specific energy states, it emits radiation with an astonishingly regular frequency, 9,192,631,770 vibrations every second. That number, so enormous and yet so steady, defines the second itself. It is the official heartbeat of the universe, as measured by humanity. Think about that for a moment. Every clock on Earth, from your phone to the satellites orbiting above, ultimately bows to the rhythm of those cesium atoms humming quietly in laboratory chambers. When you check the time, you're synchronizing yourself with an invisible chorus of atoms singing in perfect unison. It's a little humbling. Our sense of the present moment depends on something smaller than imagination can picture. An atomic clock works by counting these vibrations using microwaves, lasers, and magnetic fields. Inside its sealed chamber, cesium atoms are coaxed into resonance, the moment when their internal energy jumps precisely in tune with the driving frequency. When that resonance peaks, the system locks on, creating a standard so reliable it will not drift by more than a second in tens of millions of years. Somewhere on Earth right now, a clock is ticking so precisely that it disagrees with itself only after millions of years have passed. It's a level of consistency nature provides freely, and humanity merely learned to listen. This precision isn't just a luxury for scientists who like tidy numbers. It shapes the modern world in quiet but vital ways. The global positioning system depends on time differences between orbiting satellites and receivers on the ground. Those signals travel at the speed of light, so even a tiny timing error, just a few billionths of a second, can shift a location by several meters. Without atomic time, your phone wouldn't know which street you're standing on, your bank transfers wouldn't synchronize across continents, and the internet's global heartbeat would fall out of rhythm. Timekeeping, it turns out, isn't only about knowing when you are. It's about making sure everyone agrees. Humanity has built a vast invisible network of trust, one that unites clocks in orbit, laboratories on mountaintops, and devices in pockets, all ticking together with microscopic precision. Coordinated universal time, the grand compromise of all these measurements, is continuously adjusted to keep Earth's imperfect rotation aligned with atomic regularity. When the planet slows or speeds up slightly, we add a leap second, nudging the universe's watch back into sync. There's a strange poetry to it all. We spend our lives chasing time, yet our best machines are built to hold it still, to measure it so precisely that even the stars must yield to our precision. In the depths of a laboratory, surrounded by cables and softly pulsing lights, scientists have built devices that listen to the whispers of atoms and call it a second. In that tiny unit lies the architecture of civilization, communication, navigation, science, even the daily hum of ordinary life. And though we may never feel those billions of vibrations ourselves, they silently shape every heartbeat, every transaction, every sunrise that finds us waking to another measured day. It's remarkable, really, how all of humanity has agreed on something so fleeting, a single second defined by a dance of atoms so small that even light would envy its precision. And yet, beneath all that control and counting, the question lingers quietly. What are we truly measuring when we measure time? Imagine you are holding a stopwatch and walking slowly down a quiet road. Every step you take, the seconds on your watch tick forward in their steady rhythm. Now imagine a friend cycling past you at high speed, their own stopwatch in hand. To you, their seconds seem to tick just a little more slowly. To them, yours seem to tick just a little faster. Both of you are certain your own watch is right. And, strangely enough, you both are. This simple disagreement lies at the heart of one of the most beautiful discoveries in physics. Time is not universal. It does not flow at the same rate for everyone. Instead, it is personal, something you carry with you through space, shaped by how you move and where you stand in gravity's embrace. This personal passage through time is called proper time, and it belongs only to you. When Albert Einstein first introduced the idea in 1905, it was like tilting the universe slightly to the side. Before him, time had been absolute, a single cosmic clock ticking somewhere behind the scenes, synchronizing every event from the birth of stars to the fall of apples. But Einstein's special theory of relativity swept that notion away. He showed that there is no master clock. There are only travellers, each measuring the rhythm of the universe along their own unique path through space-time. To picture this, imagine space and time not as separate things, but as threads woven into one smooth fabric. Your life, from birth to this very second, traces a curve through that fabric, a path called a world line. Everything that moves has one. A bird swooping through the air, a planet orbiting the sun, even a beam of light, all carve their own distinct trails. The length of that trail, measured in space-time rather than ordinary distance, is your proper time. It's the clock that moves with you, the tick rate that belongs to your journey alone. The most famous way to glimpse this is through the so-called twin thought experiment. One twin stays on Earth, while the other sets off on a journey through space at near-light speed. When the travelling twin returns home, they have aged less than the one who stayed behind. To human intuition, this sounds like magic, or worse, a contradiction. But it isn't. Both twins' clocks have ticked normally according to themselves. They simply followed different routes through space-time, and one path contained fewer seconds than the other. The clocks never lied. They merely told the truth of their own experience. You can think of it like hiking across hills. Two paths may begin and end in the same places, but twist and climb differently along the way. When both hikers meet again, their pedometers may show different distances walked, yet neither has made an error. Each step counter was loyal to its owner's footsteps. Time behaves in precisely this way. Motion bends the terrain of space-time, and proper time is how far you've truly travelled through it. Even without rockets or cosmic experiments, time's elasticity touches everyday life. High-speed particles created in the upper atmosphere should decay long before they reach the ground, yet they routinely make it because their internal clocks tick more slowly as they race through the air. In particle accelerators, unstable particles live longer the faster they move. It's not because the particles resist decay, it's because time itself stretches for them. The same happens with gravity. Deep in a gravitational field, time slows down. A clock placed on the floor ticks a tiny bit more slowly than one on a shelf above it. The effect is minute, only billionths of a second, but measurable. Astronauts aboard the International Space Station, far from most of Earth's gravity but moving quickly in orbit, experience both effects at once. Speed slows their time, weaker gravity speeds it up. The balance of the two means astronauts age ever so slightly differently from people on the ground. To our senses, none of this is noticeable. You won't feel your seconds stretch while boarding a plane or compress as you climb a hill. But precision instruments can measure it easily. The world's best atomic clocks detect time dilation after just a short climb up a staircase. Walk a few meters higher, and you've already stepped into a subtly faster stream of time. Every person on Earth therefore lives at a slightly different rate from everyone else, by fractions of a second, but different nonetheless. This strange relativity of time does not mean chaos or confusion. In fact, it is one of the reasons the universe works so elegantly. Time bends just enough to keep the laws of physics consistent everywhere. The constancy of light speed, the rule that light always travels at the same speed through vacuum, forces time and space to trade flexibility. When one observer moves faster, their space contracts and their time dilates, preserving the great cosmic balance. It's as if the universe insists on fairness. All travellers experience reality in such a way that the laws remain unbroken, no matter how they move. Proper time, then, isn't an illusion or a trick, it's a personal measure of reality. Each person's clock, whether a heartbeat or an atomic pulse, simply records their unique passage through space-time. Even when two people reunite after following wildly different journeys, each clock still tells a true story. Those stories may not agree on how long the trip took, but together they describe the full geometry of the universe itself. Einstein once said that time and space are modes by which we think, not conditions in which we live. He meant that our everyday sense of time as something universal, a shared river carrying all things forward, doesn't quite match the physics beneath. Instead, the universe offers a quiet democracy of moments. Every observer, every atom, every beam of light gets its own rhythm, perfectly valid, perfectly real. You might never feel that difference in your lifetime, but the cosmos notices. From GPS satellites adjusting their signals to account for relativity, to the aging of subatomic particles in flight, the world is full of quiet corrections that keep reality in tune. Time dilation isn't a glitch in the system, it is the system. So when you look at a clock, remember that it's more than a device. It's a statement about your motion and position in the grand architecture of space-time. No clock is truly universal, and yet all of them are honest. Each one marks its own steady heartbeat, counting the moments of its own journey. Every traveller, from a drifting astronaut to someone half asleep listening to this, carries their own rhythm through the cosmos. That rhythm is the measure of proper time, the private tempo of your existence, softly beating within the universe's great symphony. Picture yourself standing on a train platform on a calm evening. A long train glides past, smooth and quiet, its windows glowing faintly in the fading light. As it passes, a bolt of lightning strikes the front of the train, and at that same instant another bolt strikes the rear. To you standing still, the flashes seem to occur at exactly the same time. Both ends of the train light up together, two bright bursts framing the moving carriages. Now imagine a friend sitting exactly halfway along the train, riding with it as it moves. When those lightning bolts flash, light from each strike rushes toward the friend through the air. But here's the twist. The train is moving forward, so the friend is moving toward the light coming from the front and away from the light coming from the rear. Even though the light from both bolts travels at the same speed, the one from the front reaches them first. From the friend's perspective, the strikes were not simultaneous at all. You and your friend both witnessed the same event, yet you disagree on the order of what happened. Who is right? Einstein's answer was simple and revolutionary. Both of you are. There is no universal now, no cosmic referee declaring what happened first. Each observer's now depends on how they move through space-time. Before 1905, scientists believed that simultaneity, the idea of events happening at the same time, was absolute. Clocks might tick differently, but now was thought to be the same everywhere, like a great invisible plane slicing across the universe, linking all events that coexist in the present. But Einstein realized that this notion couldn't survive once you accept the constancy of light speed. Light always travels at the same speed for everyone, no matter how fast you're moving. To preserve that truth, the universe must give up something else, and what it gives up is a shared, universal now. This is what the relativity of simultaneity means. The flow of time and the order of events depend on who's watching and how they're moving. The universe is not a synchronized orchestra with one master conductor. It is more like countless musicians, each keeping their own tempo, yet somehow still forming a coherent symphony. You can think of it like slicing a loaf of bread. If space-time is the loaf, then each observer's present moment is a slice. But when you tilt the knife at a different angle, you cut through the loaf in a different way. Your now might include different parts of the loaf than someone else's. Nothing changes in the loaf itself. It's the same space-time. But your perspective determines what you call the present. That means two events that appear simultaneous to you might happen in a different order for someone moving quickly relative to you. The universe allows this because the only thing everyone agrees on is cause and effect. No observer can see an effect occur before its cause. That order is preserved absolutely. But outside of that boundary, nature is wonderfully flexible. The precise order of distant, unrelated events is negotiable, a kind of cosmic courtesy extended to motion. At first, this feels deeply unsettling. Human experience depends on the idea of shared moments. We clap in time to music, we synchronize watches, we count down to midnight together. Yet physics tells us those shared moments are local conveniences, not universal truths. Every observer carves their own cross-section of the cosmos, their own personal slice of now. The consequences of this go far beyond philosophical curiosity. The entire infrastructure of modern civilization depends on managing this relativity with extraordinary care. Satellites orbiting Earth experience both time dilation and differing simultaneity compared to clocks on the ground. To make global positioning systems work, engineers have to account for these effects with exquisite precision. When your phone tells you exactly where you are, it's only possible because physicists learned how to translate between many overlapping nows. In the early days of relativity, even Einstein struggled with the psychological weight of this idea. It meant that the present is not an objective part of the universe. It's something the mind constructs from local information. Light from distant stars takes years, centuries, or even millions of years to reach us. When we look into the sky, we see countless versions of now scattered across time. Some stars we see may have already burned out, others may not yet have existed when their light began its journey. There is no universal clock uniting them. The cosmos is a patchwork of different moments stitched together by the speed of light. And yet, despite this disjointed reality, the world around us feels beautifully continuous. Our brains perform constant synchronization, stitching sensory input and memory into a seamless narrative. The relativity of simultaneity is hidden from daily life because our motions are slow and our distance is small compared to light's reach. Two people standing in the same room share a now within billionths of a second. For practical purposes, that's perfect harmony, but scale it up to stars, galaxies, or fast-moving spacecraft, and that harmony dissolves into relativity's grand mosaic. The principle of simultaneity also explains why absolute synchronization across the universe is impossible. Astronomers can coordinate telescopes on different continents to act as one giant eye, but they must rely on careful timing corrections derived from relativity. Each observatory's clock ticks according to its own gravitational field and motion, and data must be adjusted so the signals line up. In 2019, when the Event Horizon Telescope captured the first image of a black hole, it succeeded only because computers accounted for these relativistic quirks. Even our glimpses of eternity depend on understanding that there is no single eternal now. It's tempting to imagine that this relativistic universe somehow feels chaotic or disconnected, but it doesn't. The laws of physics are built precisely so that everyone's experience remains self-consistent. What changes is perspective. A moving observer's clock ticks differently, their rulers shrink, and their now tilts through space-time. But all of it conspires to make the same underlying events fit together smoothly. The universe is flexible enough to allow each viewpoint to be valid without contradiction. Einstein described this with quiet poetry. For us believing physicists, he once wrote, the distinction between past, present and future is only a stubbornly persistent illusion. He didn't mean time was fake, but that its divisions belong to our perception, not to the cosmos itself. Every observer, no matter how fast or slow, carries their own temporal perspective, a private rhythm in the grand score of the universe. So the next time you watch a distant flash of lightning or see the sun set over the horizon, remember that your now is yours alone. Somewhere else, perhaps only a few steps away, someone else's now is already tilted slightly through space-time, their version of the moment subtly different. We're all sharing the same universe, but never quite the same moment. And that's not a flaw in the design, it's part of its beauty. The cosmos isn't a single clock ticking for all, but a vast network of personal tempos woven together, each one genuine and complete. Imagine standing at the bottom of a mountain, your watch ticking quietly as you look up toward its snow-covered peak. A friend climbs to the top carrying an identical watch. When you meet again, after comparing your two clocks, something strange appears. Your friend's watch shows a slightly later time. They have aged a little faster than you, by a fraction so small it could never be felt, but so real that it can be measured. You spent the same hours in the same day, yet your experiences of time were not identical. That quiet discrepancy is one of the most elegant truths of Einstein's relativity. Time itself changes its rhythm depending on where you are and how you move. Motion slows it down, gravity holds it back. Every clock in the universe, from your wristwatch to the pulse of a star, is shaped by its journey through space-time. Einstein's early work on special relativity in 1905 revealed that moving clocks tick more slowly than stationary ones, as seen from the perspective of an outside observer. To someone travelling close to the speed of light, seconds stretch, distances shrink, and energy and time become deeply entangled. Then, a decade later, his general theory of relativity added a new twist. Gravity itself also changes the tempo of time. Massive objects like planets or stars create dents in the fabric of space-time, and in those gravitational wells, time runs slower. Think of space-time as a soft rubber sheet. A planet rests on it, bending the surface downward into a shallow bowl. Light and matter move through this curved landscape, following the natural slope. Now imagine time as a gentle current flowing across the sheet. Near the bottom of the bowl, where gravity is strongest, the current moves sluggishly, as though thickened by the planet's pull. Farther away, higher on the slope, the current flows more freely. To climb out of a gravitational field is, in a way, to step into faster moving time. This isn't metaphor alone, it's measurable reality. Scientists have confirmed it countless times with atomic clocks. In one famous experiment, a pair of identical cesium clocks was placed at different altitudes, one at the base of a tall tower, the other near the top. After running for a while, the higher clock had gained a few billionths of a second. The effect was exactly what general relativity predicted. Gravity slows time, and even the height difference between floors in a building can reveal it. You truly do age a little faster on the roof than in the cellar. This tiny stretching of time also means that light escaping from a strong gravitational field loses energy. It becomes redshifted. Imagine shining a beam of light upward from deep inside a gravity well. As it climbs, it must work against the pull of the gravitational field. It expends part of its energy to escape, and since light's energy is tied to its frequency, its colour shifts toward a red, the lower energy end of the spectrum. This phenomenon, called gravitational redshift, was first measured using precise clocks on Earth and later confirmed by observing light from stars and galaxies. Even photons, it seems, pay a toll to gravity in the currency of time. The same principle governs the behaviour of satellites orbiting above Earth. Each global positioning system satellite carries an atomic clock, synchronized with those on the ground. But the satellites orbit high above the planet, where gravity is weaker and time flows a little faster. They also move quickly around the Earth, and that motion slows their time slightly due to special relativity. The two effects compete. Weaker gravity speeds up the satellite clocks. Motion slows them down. When combined, the net result is that time on the satellites runs about 45 microseconds faster per day than time on the surface. 45 microseconds, less than the blink of an eye, but large enough that without correction, GPS systems would drift by kilometers each day. Your phone, car, and airplane navigation all rely on this delicate dance of relativity. Each satellite constantly adjusts its timing to stay in harmony with the planet below, and the algorithms that calculate your location compensate for both gravitational and velocity-based dilation. Every map you open on your screen quietly owes its accuracy to Einstein's equations. A similar effect has been seen far from Earth, where gravity becomes extreme. Near neutron stars and black holes, time dilation grows astonishing. To a distant observer, a clock near a black hole's surface seems to tick slower and slower until, at the event horizon, it appears to stop entirely. The object itself never feels its own time halting. From its perspective, everything proceeds normally. But from afar, the universe seems to watch the last moments of its fall stretched endlessly across eternity. Closer to home, we see subtler echoes of the same idea in the world of high-energy physics. Inside particle accelerators, subatomic particles such as muons are created moving at speeds close to that of light. These particles normally decay in a tiny fraction of a second, yet when moving rapidly, their lifetimes stretch. To the muon, nothing feels unusual, it simply exists for its normal span of proper time. But from the laboratory's viewpoint, the clock inside that particle is running slowly, its decay delayed by the same cosmic rule that governs satellites and mountains. What makes this concept so beautiful is its consistency. The rules of relativity apply equally to enormous galaxies and fleeting particles, to human lifespans and the glow of distant quasars. Time dilation is not a quirk. It is the natural language of space-time. Everything that moves, everything that feels gravity, experiences its own tempo. You can almost think of the universe as an orchestra performing one piece of music, but each instrument plays in its own time signature. The conductor is space-time itself, ensuring that the different rhythms align just enough to keep the melody coherent. A second on one instrument might be a slightly longer beat on another, yet the harmony remains. It's tempting to imagine that time dilation is a kind of optical illusion, a trick of perspective, but it isn't. It's built into the structure of the universe. The faster you move, the slower your clock ticks relative to someone standing still. The deeper you are in a gravitational field, the more time itself bends to the pull. There is no way to step outside and see the real time ticking somewhere else. There is only the time that belongs to your own path. Everyday experience hides these differences because the speeds and gravitational changes we live with are small. But every plane flight, every satellite orbit, every climb up a mountain quietly reveals that time is not uniform. It's elastic, stretching and shrinking in response to motion and mass. It's a humbling thought. Each of us lives in our own gently curved pocket of space-time, our seconds subtly shaped by where we stand and how we move. And even though we'll never sense it, that tiny stretch or squeeze connects us to the workings of the cosmos itself. Time is not an absolute ruler drawn through the universe. It's a living rhythm that bends to gravity and speed alike. Even gravity, it seems, keeps a schedule. Pour a drop of dark ink into a glass of water and watch what happens. At first it swirls and twists in graceful loops, tiny ribbons of colour curling and folding through the clear liquid. But after a while, the patterns blur, and the water turns an even cloudy blue. You never see the process reverse. The colour doesn't decide to pull itself back together, gathering into a neat droplet once more. The ink spreads, the order fades, and time, at least as we experience it, moves forward. This one-way journey from order to disorder, from structure to spread, is the quiet heartbeat of the universe. It's what we call the arrow of time. Physics tells us that most of nature's fundamental laws, the rules governing particles and forces, are perfectly reversible. If you filmed two atoms colliding and played it backward, the motion would look just as valid as the forward version. On the microscopic level, there is no preferred direction. But the world we actually live in is not built from two atoms. It's built from unimaginable numbers of them. And when billions upon billions of particles interact, something new emerges: probability. This is where entropy enters the story. Entropy isn't chaos or destruction, though it's often described that way. It's simply a measure of how many different ways a system can be arranged while still looking the same from a distance. A neat stack of papers has very few possible configurations. It's ordered, low in entropy. The same papers scattered across the floor can be arranged in countless ways. That's high entropy. When you zoom out, both states might appear as a pile of papers, but one hides far more microscopic possibilities than the other. Nature tends to move towards states that are more probable, and high entropy states are the most probable of all. It's not a rule of force, but of counting. There are vastly more ways for ink molecules to mix evenly than there are for them to stay separated. There are infinitely more ways for air to spread throughout a room than for it to huddle politely in one corner. So while the laws of motion allow the reversed version, the unmixed ink, the unspilled perfume, the unbroken egg, it's so statistically unlikely that you could wait longer than the age of the universe and never see it happen. Physics doesn't forbid it. It just makes it embarrassingly unlikely. The arrow of time, then, isn't written into the fundamental equations. It arises from the overwhelming bias of probability. When we talk about heat flowing from hot to cold, ice melting, or a cup of coffee cooling down, we're watching entropy at work. Energy spreads out, temperatures even out, and the universe quietly maximizes its options. It's the same story in every corner of reality, from the drifting of galaxies to the fading of footprints in sand. But if the microscopic rules are reversible, why does the macroscopic world only move one way? The answer lies in what physicists call coarse graining. Imagine you're looking at a painting up close, able to see every brushstroke. At that scale, you can reverse the order of the strokes and still have a coherent image. But step back far enough that individual strokes blur together, and you begin to see an overall direction, colours fading, forms softening, the composition changing. In thermodynamics, we don't track every molecule individually, we average over them. This act of averaging blurs the reversibility that exists at smaller scales, revealing the one-way flow of time that we experience. Our experience of memory, cause and effect is deeply tied to this arrow. You remember the past because it left physical traces, patterns of low entropy that can be recorded. A photograph captures light that once struck a surface. The reaction created a permanent mark. But the future leaves no such record, because it hasn't happened yet, and entropy hasn't yet had the chance to scatter its clues. In a low entropy state, structure and information can be preserved. As entropy rises, those records dissolve into randomness. Memory is simply an organised remnant of order. Consider an egg sitting on a kitchen counter. Inside, the yolk and white are neatly separated, molecules arranged in delicate structures built by biology. Drop it on the floor, and in a blink, the order disappears. The egg breaks apart, the molecules mix, and entropy soars. You never see the reverse, a splattered egg leaping back into its shell, because that would require all the jumbled molecules to coordinate perfectly at the same moment. It's not impossible in principle, but the odds are so absurdly tiny that it might as well be. It's as if the universe would have to get together and agree, let's do that again, backward, and it never does. The same principle shapes everything from weather systems to human history. A house takes effort to keep tidy because order is special. It's a small island in a vast sea of possible disordered states. Entropy isn't out to get you. It's just what happens when energy and matter are left to their own devices. A hot cup of tea will cool down on its own. but it will never spontaneously reheat itself, because the energy disperses among air molecules in countless ways, and almost none of those ways involve the tea becoming warmer again. On the scale of the cosmos, the arrow of time unfolds through grander versions of these same patterns. Stars burn hydrogen into helium, releasing energy and light that scatter through space. Galaxies form, merge, and drift apart. The universe as a whole trends toward greater entropy, a slow, graceful spreading of energy and matter. This does not mean chaos or decay so much as diffusion, the universe exploring every possible arrangement it can. There is something quietly poetic about that. Entropy ensures that no moment is ever perfectly repeatable. Each second carves a path that cannot be retraced, not because nature forbids the backward step, but because probability drowns it in possibility. Time, as we know it, is the name we give to that unstoppable broadening of the universe's options. And yet, while entropy makes the world less ordered, it also allows complexity to exist. The flow of heat from hot to cold, the slow release of stored energy, creates the conditions for life and thought. Stars, planets, chemistry, and even consciousness emerge in the gradients between order and disorder. Life thrives on the difference between the two, feeding on energy as it flows down the slopes of entropy. In a perfectly uniform, fully entropic universe, nothing could change, and without change, there would be no time to feel at all. So the arrow of time is not an enemy of life. It's the very thing that makes life possible. It grants direction to a universe that might otherwise drift in aimless symmetry. From the melting of ice to the growth of galaxies, from the decay of atoms to the flicker of thought, entropy guides everything forward. One day, if the universe reaches perfect equilibrium, that arrow may fade, and time itself might lose its meaning. But for now, it still points steadily ahead, carried in every breath, every heartbeat, every sunrise that follows another. Entropy is the quiet sculptor of the cosmos. It takes the reversible laws of physics and turns them into the one-way story we call experience. It whispers the reason coffee cools, why we age, why memories live in the past and not the future. If you could watch the tiniest events in nature, particles colliding, decaying, and reforming, you might expect that the universe would look just as ordinary in reverse. A movie of two billiard balls colliding on a table is perfectly believable played backward. The laws of motion allow either direction. In much the same way, the fundamental equations of physics are mostly time-symmetric. They do not care which way the clock runs. Yet somewhere deep inside the subatomic world, nature hides a small and stubborn preference, a faint tilt in time's mirror. To understand it, we need to talk about three kinds of symmetry that physicists love: C, P, and T. C stands for charge conjugation, which imagines swapping every particle for its antiparticle, protons for antiprotons, electrons for positrons. P is parity, the symmetry of reflection. It asks, if the universe were flipped in a mirror, would the laws of physics look the same? T is time reversal, the notion of running the cosmic film backward. Together these symmetries describe the universe's sense of fairness, change charges, flip directions, or rewind events. Shouldn't nature behave identically? For a long time, physicists thought the answer was yes. Then, piece by piece, the universe began to show its quirks. In 1956, experiments revealed that the weak nuclear force, the one responsible for radioactive decay, does not obey parity. When certain atomic nuclei decay, the emitted particles have a distinct handedness. They prefer one spin direction over the other. It was as if the mirror image of the process belonged to a different world altogether. A year later, scientists confirmed that charge conjugation symmetry was also broken in the weak interaction. The universe, it seemed, knew its left from its right, and its particles from its antiparticles. But the truly intriguing story began in 1964, when James Cronin and Val Fitch studied a strange particle called the kaon. Kaons come in two varieties, one that decays quickly and one that decays more slowly. According to the rules of C&P symmetry, one should transform neatly into the other if you swap matter for antimatter and reflect space. Yet when the researchers examined the decays, they found something unexpected. A tiny fraction of long-lived kaons decayed in ways that violated this rule. It was as though the mirror version of the event didn't quite match. This discovery became known as CP violation, C for charge, P for parity. It meant that the universe distinguishes between left and right, and between matter and antimatter simultaneously. And because of a deep mathematical relationship known as the CPT theorem, breaking CP symmetry implies a corresponding break in time reversal symmetry as well. In other words, the laws governing these tiny particles look ever so slightly different when time runs backward. That difference is minuscule, so small that it's drowned out by the vast balance of all other processes, but its implications are profound. Somewhere in those delicate imbalances may lie the reason we exist at all. When the universe was young and unimaginably hot, energy condensed into particles and antiparticles in equal amounts. They should have annihilated one another completely, leaving behind a uniform bath of light and nothing else. Yet here we are, made of matter, not antimatter, living in a universe where every star, planet and cell depends on that ancient imbalance. Out of roughly every billion matter-antimatter pairs, one extra particle of matter survived. Why? Physicists suspect that CP violation holds part of the answer. The slight bias in the weak force could have tilted the cosmic scales just enough for a tiny surplus of matter to remain after most of it annihilated. Over billions of years, that leftover matter gathered into galaxies, stars and people, wondering why coffee cools down but never warms up on its own. To date, CP violation has been observed not only in kaons, but also in heavier particles called B mesons. These exotic combinations of quarks exhibit similar asymmetries in how they decay. Although the effect is small, it shows that time symmetry isn't perfect at the microscopic level. In principle, if you could watch a movie of certain particle interactions and then play it backward, you could tell which version was the real one. The laws themselves would betray the difference. This subtle preference for one direction of time is not the same as the thermodynamic arrow we live with every day. Entropy's arrow arises from probability, from the statistical tendency of things to spread and mix. CP violation, by contrast, is written into the mathematics of the weak force itself. It's not about disorder or memory. It's about how nature's building blocks dance ever so slightly out of step with their reflections. It's a microscopic tilt, almost imperceptible, but crucial to the universe's story. Interestingly, if you combine all three transformations, C, P and T together, the laws of physics appear to balance again. This CPT symmetry is believed to be absolute. It ensures that even if charge, parity or time individually fail to hold, the combination of all three restores perfect fairness. That delicate balance hints at something deep and elegant in the structure of reality, a cosmic promise that for every asymmetry, there's a hidden harmony keeping the whole universe consistent. The presence of time asymmetry at the smallest scales also invites philosophical reflection. If the universe is slightly biased, what does that say about time itself? It reminds us that time isn't just a human convenience or a psychological arrow. It's embedded, in some way, in the very language of nature. Even in realms where equations are clean and reversible, reality adds a whisper of direction, an unspoken preference for forward. It's an astonishing thought that the fate of everything, galaxies, atoms, people, may trace back to a subtle imperfection in an otherwise symmetrical universe. A few particles failing to behave in mirror-perfect fashion may be the reason the cosmos has structure at all, rather than an empty sea of light. That tiny tilt gives us a past distinct from a future, a world that can unfold rather than replay itself endlessly. In the laboratory, these violations are so rare and fleeting that they require extraordinary experiments to detect. Particle accelerators the size of cities produce billions of collisions per second just to catch a handful of asymmetrical decays. Yet in those rare moments, physicists glimpse something fundamental, a clue that time, at the deepest level, may not be an impartial spectator. Most of nature's laws still treat past and future as equals. A pendulum swings symmetrically, light waves ripple identically forward and backward, planets orbit according to timeless equations. But in the faint domain of unstable particles, the arrow of time takes on a literal meaning, written into the probabilities of decay. Imagine pressing pause on the universe, everything, every star, planet and heartbeat frozen in an instant. What would that single frame look like? Now imagine unpausing, letting the frame blend smoothly into the next and the next after that. To us, that motion feels like the passage of time, a steady unfolding of now. But according to relativity, those frames are all equally real. The universe doesn't scroll from one moment to the next. All the frames exist together, already laid out in a vast four-dimensional structure called space-time. This idea is sometimes called the block universe, and it is one of the most quietly radical ways of seeing reality. In the block view, time doesn't flow. Instead, the past, present, and future all coexist, like pages of a book that have already been written. When you flip through a novel, the ending is as real as the beginning, you just haven't read it yet. Similarly, every event in space-time, from the birth of a star to the blink of an eye, already occupies its own coordinates in the cosmic map. To most of us, this feels strange, even a little unsettling. Our intuition insists that only the present is real, the ticking clock, the sound of your breath, the words you hear right now. This perspective, called presentism, holds that the past no longer exists and the future is yet to be born. It's the natural human view, and it's hard to imagine living any other way. After all, we experience life as a sequence of moments, not as a completed tapestry. But Einstein's theory of relativity quietly undermined that comforting sense of universality. It showed that the division between past, present and future isn't absolute. It depends on the observer. Two people moving differently through space will slice space-time into nows that don't line up. What is the present for one observer might be part of the past or future for another. Once that realization takes hold, it becomes difficult to insist that there's a single objective moment we all share. Instead, every observer has their own personal cross-section of the universe's timeline. Einstein himself hinted at this profound shift when he wrote that the distinction between past, present and future is a stubborn illusion. He didn't mean that time is meaningless, but that the way we divide it into before, now and after is more a feature of human perception than of physics. The universe, as seen by relativity, doesn't grow or age. It simply is. Visualize space-time as a grand landscape. A mountain stands for a cluster of events, perhaps the life of a star. A valley might represent quieter periods of cosmic calm. We, as conscious travellers, move along a path through that terrain, perceiving one ridge or valley at a time. But from a higher vantage point, the entire geography already exists. Our motion doesn't create the landscape, it merely reveals it piece by piece. This picture, sometimes called eternalism, has fascinated philosophers and physicists alike. It suggests that all moments, every joy, every discovery, every goodbye are already there, woven into the fabric of space-time. The birth of the universe and its far future are just different regions of the same four-dimensional whole. From the perspective of physics, the cosmos doesn't need a clock to tick. All its events are arranged in relation to one another, forming a single, unchanging structure. But here's the puzzle. If everything is already laid out, why do we feel time moving? Why does the present seem to glide along the timeline, dragging us from memory into anticipation? The answer may lie not in physics, but in consciousness itself. Our brains, like movie projectors, play the static frames of space-time one after another, creating the illusion of motion and change. In this analogy, the film reel already contains the ending, yet the story still feels alive frame by frame. In daily life, this illusion is essential. Without the sense of flow, we couldn't learn, plan, or experience meaning. It's how our minds interpret the structure of space-time, turning static geometry into a living narrative. The block universe may be fixed, but our awareness travels through it, lighting one frame after another with experience. Some scientists suggest that this perceived motion might even emerge from the way memory works. We remember the past because our brains contain physical records of it, patterns of neurons that encode previous states. But we don't have memories of the future. This asymmetry gives the impression of a moving now. The universe itself isn't changing, but our information about it is. Every moment contains records of earlier ones, but not of those yet to come. Our consciousness rides that gradient of information, and the result feels like the passage of time. There's a quiet beauty in this perspective. It means that every moment you've lived, every conversation, every breath, every star you've ever looked at still exists, etched somewhere in space-time. The past hasn't vanished. It's simply another region, unreachable from here. The same is true of the future. It's already there, waiting, though we cannot yet perceive it. Critics of the block universe argue that this view makes free will difficult to reconcile. If the future already exists, how can we choose it? But others see it differently. From inside the story, every choice still feels genuine, because our experience of decision-making is part of the block itself. The universe includes not just outcomes, but the living process of choosing them. The feeling of freedom, the uncertainty of what's next, these too are events written into the structure. The book includes both the plot and the reader's emotions. There's also comfort in thinking that the people and moments we've lost haven't been erased from reality. They still occupy their coordinates in space-time, perfectly preserved in the cosmic geometry. You can't visit them, but they remain part of the universe's timeless architecture. For a physicist, that permanence can feel strangely compassionate. Nothing truly disappears. It only becomes another page further back in the book. At the same time, the block universe doesn't deny our lived sense of motion. It just tells us that the flow we feel is local, not universal, a phenomenon born of perspective. Physics gives us the structure, consciousness provides the rhythm. The two coexist gracefully, each describing the same reality from a different angle. You could say that the block universe is the symphony's sheet music, already written in full, while our awareness is the performance, the melody unfolding in time. Both are real. One is static and eternal, the other dynamic and felt. The score doesn't move, but the song still plays. So while the equations of relativity may freeze time into a single, four-dimensional sculpture, our minds bring it back to life, one heartbeat at a time. We are both inhabitants and interpreters of that cosmic geometry, reading it line by line, frame by frame. Every clock humanity has ever built, pendulum, quartz, atomic, has been an imitation of something greater. Long before the first ticking gears, the universe itself kept time. It just did so in silence. There are no hands or dials in the cosmos, no bells marking the hour. Instead, the universe measures its own age through its expansion, its cooling, and the faint light left over from its fiery beginning. The cosmos doesn't wear a wristwatch. It glows with memory. If you were to ask the universe how old it is, it would answer not in words, but in temperature. That temperature is written in the light of the cosmic microwave background, a soft afterglow that fills all of space. This radiation is the echo of the Big Bang, stretched and cooled over billions of years as the universe expanded. Today it glows at just 2.7 degrees above absolute zero, a whisper of the original blaze. Every direction you look, this same gentle microwave light greets you. uniform to 1 part in 100,000. It's as if the cosmos itself carries a faint memory of its childhood, still shining, still measurable. When this light was first released, the universe was about 380,000 years old, a mere infant by cosmic standards. Before that time, the cosmos was opaque, filled with a plasma so dense that light could not travel freely. As the universe expanded and cooled, atoms formed and photons were suddenly free to roam. They've been travelling ever since, stretched by the expanding fabric of space. Their wavelengths lengthened until they became microwaves. By studying this glow, scientists can read the early universe's conditions with astonishing precision. Tiny variations in its temperature map show the seeds of galaxies, the fingerprints of quantum fluctuations magnified by time. In a sense, the cosmic microwave background is the universe's oldest photograph, a snapshot of its face when it first became transparent. When we look at it through radio telescopes, we're not seeing a picture painted later. We're receiving light that has been travelling for 13.8 billion years, reaching us now after an unimaginable journey. It's the most reliable clock we have, because it doesn't just measure time, it is time, preserved as radiation. Beyond that first glow, the expansion of the universe acts as a kind of cosmic metronome. Galaxies drift apart, and the rhythm of that drift carries information about the universe's history. When Edwin Hubble discovered in 1929 that distant galaxies are receding from us, he found that their speed is proportional to their distance. The farther away they are, the faster they flee. This simple relationship, known as Hubble's law, gave scientists the first clue that the universe was once smaller, denser, and hotter. By tracing that expansion backward, they could estimate when it all began, the moment when everything we now see was compressed into a single point of unimaginable energy. Today, the expansion rate is measured with exquisite precision using telescopes and space observatories. The Hubble constant, as it's called, defines how fast the universe stretches. Like a ticking heartbeat, it marks the tempo of cosmic history. And yet, even this metronome isn't perfectly steady. Observations show that the expansion is accelerating, driven by something mysterious we call dark energy. It's as if the cosmic clock has begun to speed up, its rhythm quickening with age. When astronomers measure distant galaxies, they aren't just mapping space, they're mapping time. Because light takes time to travel, the farther away something is, the further back in history we see it. The light from the Sun is 8 minutes old by the time it reaches Earth. The light from the nearest major galaxy, Andromeda, began its journey 2.5 million years ago. The faintest galaxies visible to our best telescopes show us what the universe looked like over 13 billion years ago, when the first stars were just beginning to shine. Looking out is the same as looking back. Every photon is a messenger from the past, carrying information about where and when it was born. It's easy to forget that the night sky is not a single moment in time. Each star you see belongs to a different era. Some may have already burned out, others may not even have formed yet in our current now. The cosmos is a layered archive, every patch of sky containing light from a different chapter of the same story. The concept of now loses its meaning when distances are measured in billions of light years. The universe tells its tale all at once, and we, from our tiny vantage point, translate that timelessness into a sequence. Determining the age of the universe, 13.8 billion years, is one of the triumphs of modern cosmology. Scientists reach this number not by turning a clock forward, but by reading multiple cosmic timepieces, the expansion rate, the brightness of ancient stars, the abundance of light elements like helium and deuterium, and the pattern of ripples in the cosmic microwave background all point to the same conclusion. It's remarkable that by listening to light, measuring distances and comparing models, we can reconstruct the universe's entire lifespan from its earliest whisper to its present quiet hum. And what a quiet hum it is. The The background radiation that once roared with the heat of creation now fills space like a faint static, energy diluted by expansion, but still perfectly even. If you could tune an old television to an unused channel, a small fraction of that fuzzy noise between stations would be the universe itself, speaking from its first moments. The cosmic clock keeps ticking not in seconds or minutes, but in the slow drift of galaxies and the cooling of space. Every billion years or so, the temperature of the cosmic background drops ever so slightly. The light that once burned white hot now stretches toward ever longer wavelengths, losing energy as the universe grows. It's a process that has no hurry, no pause button, and no reset. Time on this scale is almost indistinguishable from change itself, yet even in its vastness, the universe remains surprisingly consistent. The same physical laws that govern your heartbeat also govern the orbit of galaxies. The same arrow of time that melts an ice cube on Earth guides the cooling of the cosmos. Everything, from atoms to superclusters, marches to the same thermodynamic rhythm, though at very different tempos. There's something profoundly humbling about realizing that timekeeping isn't our invention, it's a property of existence. The Earth spins, the Moon orbits, the Sun burns, galaxies expand and the background light cools. All these cycles, motions and transformations are forms of cosmic counting. We simply borrowed them to measure our days and years. In the end, when you gaze into the night sky, you're seeing the universe's diary, each star a paragraph, each galaxy a chapter, each photon a single letter written long ago. Together they tell the story of how time itself has unfolded since that first blinding dawn. The cosmos doesn't need a clock to know its age. It has been keeping time all along, written in light, woven in expansion, remembered in its faint and endless glow. When you look back toward the beginning of the universe, something extraordinary stands out. The early cosmos was smooth, hot, and simple, and yet, in a very important sense, it was profoundly ordered. That might sound strange. A universe full of roaring radiation and dense plasma doesn't seem like a calm or structured place, but from the perspective of entropy, it was astonishingly tidy. This early neatness, this low entropy beginning, is what set the direction for everything that followed. It's the origin of the arrow of time. To understand why, imagine painting on a blank canvas. The first brushstroke immediately creates contrast, structure, something that wasn't there before. Before that moment, the canvas held pure potential. In much the same way, the newborn universe was a pristine field, almost perfectly uniform, yet that very smoothness was an incredibly special, improbable state. The laws of physics themselves didn't demand it. They simply began from it. The early universe wasn't in thermal equilibrium. It was a starting line, not a resting place. At around 380,000 years after the Big Bang, when the cosmic microwave background was released, the universe's temperature was about 3,000 degrees. It was almost the same everywhere. Differences from one region to another were less than 1 part in 100,000. That extraordinary smoothness meant low entropy, at least in the gravitational sense. Matter and radiation were spread evenly, without the clumps and structures that later became galaxies, stars and planets. Gravity, which tends to pull matter together, was poised and waiting. Here's where things get subtle. In most physical systems, uniformity corresponds to high entropy. A gas evenly filling a room is more disordered than one confined to a corner, but gravity behaves differently. For gravity, uniformity means low entropy, because the natural tendency of matter under gravity is to clump together. A uniform spread of mass is a precariously balanced arrangement, a special condition that will inevitably give way to structure. When that balance breaks, entropy increases. The universe's smooth beginning, then, was not the peak of disorder, but the calm before the cosmic storm. Once gravity began to sculpt the universe, it set the arrow of time into motion. Slight irregularities in density, tiny ripples in the otherwise uniform plasma, grew slowly under the pull of gravity. Over billions of years, those ripples became galaxies, stars, and planets. Entropy increased as matter fell together, radiating energy outward. Every collapsing cloud of gas, every glowing star, every swirling galaxy was gravity's way of turning order into complexity and complexity into disorder. From that perspective, the expansion of the universe isn't just a stretching of space, it's a spreading of possibilities. As space grew, so did the room for entropy to increase. The universe cooled, but it also diversified, producing countless ways for matter and energy to arrange themselves. That growth of complexity is the signature of an arrow, one that points away from the early simplicity toward the rich, tangled cosmos we inhabit now. The great puzzle is why the universe started so smooth in the first place. The laws of physics describe how things evolve from one state to another, but they don't explain why the initial conditions were what they were. Entropy's arrow depends on starting low and moving high, but nothing in the equations insists on that particular beginning. It's as though we opened a book already halfway written and found the first page inexplicably pristine, waiting to be marked. Some physicists suspect that cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang, helped set that condition. Inflation would have stretched out any initial irregularities, ironing the universe into near-perfect smoothness. But even that explanation raises another question. Why did inflation start in the first place? And under what circumstances? What gave rise to the special, low-entropy state that allowed everything else to unfold? Others explored deeper possibilities, suggesting that our universe may be part of a larger multiverse, with each region starting with different physical parameters and entropic histories. In that vast landscape, perhaps we simply inhabit a pocket where entropy began low enough to produce observers capable of asking these questions. It's a thought that feels both grand and humbling, an attempt to turn cosmic coincidence into cosmic context. Still, the mystery remains unsolved. We can trace the arrow of time back through the history of stars and galaxies, back to the earliest atoms and the smooth fireball of the Big Bang. But just before that, the trail goes cold. The universe seems to have emerged already biased toward order, like a clock that started with all its springs tightly wound. Every second since has been the gradual release of that stored potential. This idea reshapes how we think about beginnings. The low entropy of the early cosmos wasn't merely a blank slate, it was a condition of exquisite balance, almost too perfect to last. It's what allowed structure, chemistry, and life itself to exist. Without that initial order, everything would have been thermal chaos from the start, with no arrow to follow and no story to tell. When we look up at the night sky, we're seeing the aftermath of that initial imperfection, the tiny irregularities that broke the symmetry and gave rise to galaxies. The glow of the cosmic microwave background still carries the imprint of those fluctuations, the first seeds of complexity. Each faint ripple in that ancient light marks the beginning of a journey, from smoothness to structure, from simplicity to stars. There's a quiet irony in the way entropy governs beauty. The increase of disorder gave birth to order in forms we can perceive, the shapes of clouds, the spiral arms of galaxies, the chemistry of life. The universe's tendency toward greater entropy created pockets of temporary structure, islands where energy could flow and complexity could bloom. Even our own minds, capable of pondering these vast questions, are products of that same drift toward disorder. We are patterns in the tide of entropy, fleeting but significant. It's possible that one day the universe will reach equilibrium, when everything has spread out too far for new structures to form. The arrow of time may then fade, replaced by a vast stillness where nothing much happens. But for now, we live in the middle chapters, when gravity still pulls, stars still burn, and life still asks why. When cosmologists simulate the early universe, they often describe it as a smooth field dotted with tiny fluctuations, a cosmic canvas waiting for paint. The galaxies and clusters we see today are brushstrokes on that canvas, drawn by time and gravity working together. From the faintest background glow to the brightest star, everything we see is a record of entropy's patient climb. The question of why it all began so perfectly remains one of the deepest puzzles in science. Perhaps there is no deeper reason. Perhaps the universe simply started that way. Or perhaps the low-entropy dawn hides a principle we haven't yet discovered, a clue to why time points in one direction at all. Whatever the answer, that first, improbable state was the spark that made everything else possible. A smooth, silent universe became restless. Structure emerged, stars ignited, galaxies spun. Entropy began its long ascent, and every tick since then has been the sound of disorder blossoming. At the smallest scales of reality, time begins to behave like a polite suggestion rather than a law. The equations that describe the quantum world don't tick like clocks. They hum, standing still yet full of possibility. Deep within that stillness lies one of the most puzzling questions in all of physics. Does time truly exist, or is it something that emerges only when we look closely enough? When physicists tried to combine quantum mechanics with Einstein's general relativity, the great project known as quantum gravity, they encountered a strange silence in their equations. In the 1960s, John Wheeler and Bryce DeWitt developed an equation meant to describe the universe as a whole. It's known simply as the Wheeler-DeWitt equation, and it has one haunting feature. It contains no time variable at all. It doesn't say how the universe changes, it just describes a static wave function encompassing every possible configuration of space and matter. It's as if the entire cosmos were frozen, a single, timeless whole. This problem of time isn't a flaw in the mathematics, it's a clue. When you treat the entire universe as one quantum system, there's no outside clock to tick against it. Time, as we usually think of it, requires something to change relative to something else. If the universe is everything, there's nothing external for it to change with respect to. So, within the grand equation, motion, evolution, and history simply vanish. The universe doesn't evolve, it is. That sounds unsettling, but it may point to a deeper understanding of what time really means. Physicists like Don Page and William Wouters propose that time might not be a fundamental background at all. It could arise from relationships between parts of the universe. In their view, the universe as a whole is static, but subsystems within it can act as clocks for one another. Change is real, but only when you compare one part to another. Imagine a vast orchestra frozen in a single chord. If you could listen to the entire sound at once, it would seem eternal, unchanging. But if you focus on just a few instruments and listen to how their notes shift relative to each other, you'd begin to hear rhythm and melody. The whole symphony might be timeless, but inside it, time emerges as harmony, patterns within the stillness. That is the essence of relational time. Instead of a cosmic stage on which events play out, time becomes the relationship among those events. You know something has changed not because an external clock told you so, but because one part of the universe looks different relative to another. A pendulum swinging, a planet orbiting, or a particle decaying, all are comparisons, correlations within a larger whole. It's a subtle but profound shift in perspective. We often imagine the universe as a movie projected frame by frame. Relational time suggests there is no projector and no separate film reel. The frames are patterns of correlation, and our sense of flow is how those patterns unfold relative to one another. The universe may not move through time, we may move through correlations. This way of thinking aligns naturally with the quantum world, where measurement and interaction define what can be said to exist. Quantum mechanics describes probabilities, not certainties, and those probabilities change when systems interact. Without interaction, without relation, nothing truly happens. In that sense, time is not an independent current carrying events forward. It is what we call the network of change when systems communicate information to one another. The page-routers idea even allows for a kind of built-in observer. You, for example, are a collection of matter and energy that keeps an internal rhythm. Biological and neurological clocks comparing signals from your environment. You can experience the unfolding of moments because your brain acts as a relational system, measuring its own changing correlations with the world around it. If consciousness is a pattern of comparison, then perhaps time is too. Some experiments hint at how quantum mechanics can blur our classical sense of sequence. In a class of studies known as indefinite causal order, physicists have arranged situations where two processes happen in no fixed order. For instance, imagine two events, A and B, where one normally must precede the other. Quantum mechanics allows a setup where A happens before B and B happens before A. Both sequences exist simultaneously in a kind of superposition. Only when the system is observed does the apparent order crystallize. Cause and effect, it seems, can dance instead of march. This isn't time travel or paradox. It's simply the quantum world refusing to pick a direction until it must. What we experience as a fixed timeline could be the large-scale average of many such microscopic dances, smoothed out by decoherence and scale. On the level of individual particles, the concept of before and after can dissolve, replaced by the web of probabilities that only later assembles into familiar order. If that sounds abstract, think of it this way. The universe may not have a master clock hidden somewhere in its machinery. Instead, it may contain countless tiny clocks, each system comparing its state to others, all giving rise to a consistent sense of progression. When those comparisons align, we get the illusion of a single universal time. But underneath, the rhythm is local and relational, a mosaic rather than a melody. Even the Wheeler-DeWitt equation, though silent about time, carries within it the potential for such relationships. Within that timeless wave function, there are regions that can act as reference frames for others. Once you decide that one subsystem will serve as a clock, you can describe how the rest of the universe evolves relative to it. Time reappears, not as a cosmic constant, but as a convenient language for comparing change. This idea brings a kind of gentle humility to physics. It suggests that time might not be an ingredient of the universe, but a description of how we perceive the universe from within. Perhaps there is no ticking cosmic metronome at all. Only the music we hear when one pattern resonates against another. If you step back and look at the big picture, it becomes oddly peaceful. The universe, in its entirety, may be timeless, a vast, silent symmetry containing all possible moments at once. Yet within that stillness, relationships form, evolve, and fade. Stars burn, planets orbit, lives unfold, all as local expressions of correlation. From the perspective of eternity, nothing happens. From within, everything does. It's tempting to think of this as cold or mechanical, but it has a quiet beauty. It means that the universe isn't a machine grinding forward in time, it's a pattern eternally present, whose parts shimmer and shift in relation to one another. Time, then, is the poetry written in those shifting connections, the rhythm that appears when stillness begins to sing. Quantum mechanics, so often portrayed as chaotic or mysterious, might instead be serenely consistent. It tells us that what we call change is simply the play of relationships, and what we call time is how we notice them. On the deepest level, the universe may not be counting seconds, it may just be relating. The result is both humbling and strangely reassuring. It reminds us that we too are part of those relationships. We are patterns within the pattern, correlations within the grand equation, and as we measure, compare, and remember, we create our own local time, our own small rhythm in the timeless whole. If you could zoom in far enough on reality, the world would start to look like a shimmer of possibilities rather than solid facts. An electron might be here or there, spinning up or spinning down, existing in several states at once like a note that hasn't yet chosen its pitch. Quantum mechanics describes this strange superposition beautifully. But it leaves us with a haunting question. If everything at its core is fuzzy and uncertain, why does the world around us feel so definite? Why do we never wake up to find a chair that's in two places or a cat that's both awake and asleep? The answer, as it turns out, comes from the universe's greatest organizer, the environment. Quantum mechanics may allow for endless superpositions, but the environment hates clutter. Every particle, every photon, every molecule of air acts like a witness, constantly measuring and recording the systems it interacts with. This steady interaction wipes away the delicate quantum fuzziness, leaving behind the crisp, classical world we know. It's a process called decoherence, and it's how the universe tidies up its own quantum mess. To understand decoherence, imagine a quiet pond. Drop a single pebble and ripples spread evenly across the surface, perfect and symmetric. Now drop another pebble, and the ripples overlap, forming intricate interference patterns. That's superposition, the blending of multiple quantum possibilities. But now imagine a rainstorm, millions of droplets hitting the surface at once. The interference patterns vanish into random splashes. The ripples still exist, but they're drowned in the noise of countless interactions. That's decoherence in action, the graceful patterns of superposition smudged by the environment's relentless touch. In the quantum world, every system, an atom, a molecule, even a speck of dust, is constantly interacting with its surroundings. These interactions entangle the system with the environment, sharing information between them. As a result, the system's quantum state becomes inseparably linked with the states of everything around it. When that happens, the system no longer behaves as an isolated wave of probabilities. It becomes part of a larger classical picture. The environment effectively keeps a record of what's going on, and those records create the stable reality we experience. Decoherence doesn't destroy quantum possibilities, it hides them from view. The other branches of reality are still there, but they no longer interfere with one another. Each possible outcome evolves independently, like parallel melodies that can't be heard in the same room. To an observer within one branch, it appears as though a single, definite outcome has occurred. In truth, the universe has merely sorted its overlapping probabilities into separate, non-interacting narratives. This view replaces the old idea of wave function collapse with something subtler and in a way more elegant. Nothing dramatic happens, no mysterious leap from uncertainty to certainty. Instead, coherence gently fades as quantum systems share their information with the environment. What we call collapse is really just the moment when a system becomes entangled with so much around it that its alternatives can no longer interfere. The quantum fog condenses into classical dew, each droplet a consistent world with its own clear history. You can picture decoherence as the universe filing its paperwork. Every interaction leaves a trace, tiny imprints in the air, the light, or the radiation that fills space. When a photon bounces off a table, it carries away information about the table's shape and colour. When billions of photons do this every second, the table's position becomes effectively permanent. Anyone who looks will see it in the same place, because the environment itself has recorded that fact and shared it everywhere. Reality, in this sense, is the most public of records. The same principle applies to memory and observation. When you look at something, light from it interacts with your eyes, setting off chemical reactions in your retinas. Those reactions create electrical signals in your brain. Another layer of entanglement, another record. Your brain then stores the information as a pattern of neural activity. By the time you've noticed the object, the universe has already made 1,000 copies of that information, in photons, in heat, in your own neurons. Observation doesn't cause collapse. It simply means the environment has reached a consensus. This explains why the past feels stable. Once decoherence has locked in a record, once enough environmental witnesses agree on what happened, it becomes impossible to erase the event. You can't unbounce all the photons that scattered from a scene or disentangle the air molecules that recorded its vibrations. The universe remembers. In that sense, decoherence gives birth not just to the classical world, but to the very concept of memory and history. It's tempting to think of decoherence as a process that happens only in fancy laboratories or near the quantum limit, but it's happening everywhere, all the time. A grain of dust floating in sunlight decoheres in less than a trillionth of a second as billions of photons and air molecules interact with it. A human body decoheres unimaginably faster. The world's apparent solidity isn't because quantum mechanics fails, it's because decoherence succeeds. Yet even in its quiet efficiency, decoherence doesn't eliminate wonder. It tells us that the universe is a kind of storyteller. Each interaction writes a sentence in the book of reality, and the more witnesses there are, the harder it is to revise the text. The macroscopic world is simply the version of that story that has accumulated the most signatures. Quantum mechanics, neat freak by environment. There's an elegance to how this order arises without anyone directing it. Decoherence doesn't require conscious observation or special intervention. It's built into the fabric of interaction itself. Whenever two systems exchange information, they trade uncertainty for record keeping. The more they interact, the more stable their joint reality becomes. The result is a universe that's both quantum and classical at once. Quantum underneath, classical on the surface, held together by the constant chatter of matter and energy. And while the process is almost instantaneous for large systems, it's not absolute. In the tiniest, most isolated experiments, scientists can delay decoherence, keeping particles in superposition long enough to perform delicate manipulations. Quantum computers rely on this fragile balance. Their qubits can exist in overlapping states of 0 and 1, harnessing interference to perform many calculations at once. But the slightest nudge from the environment, a stray photon, a whiff of heat, wipes out that advantage. In a sense, the biggest obstacle in building quantum machines is the universe's obsession with cleanliness. For everyday life, though, we can be grateful for decoherence's efficiency. Without it, reality would shimmer and split constantly, never committing to a version we could inhabit. The solidity of a chair, the persistence of a memory, the reliability of cause and effect, all depend on the universe's ability to smooth away quantum ambiguity. Every touch, every beam of light, every whisper of air is a cosmic vote for definiteness. In the morning, when fog settles into distinct droplets on a leaf, it feels peaceful and inevitable. Decoherence is like that. The haze of possibility condenses into tangible reality, giving form to a world that remembers its own choices. And just as dew dries and reforms, the process never truly ends. Quantum systems continue to interact, to entangle and disentangle, keeping the universe's record book up to date. Every moment is a new page, filled not with equations but with interactions, tiny exchanges of information that keep the story consistent. So the next time you marvel at how solid and dependable the world seems, remember that underneath it all lies a restless ocean of probabilities, constantly being tamed by the environment's touch. The world you know isn't the absence of quantum strangeness, it's the result of the universe's remarkable housekeeping. We like to think of solids as timeless things, a table, a window, a rock, objects that seem immune to the slow drift of seconds. But even the most rigid matter quietly keeps time in its own way. Inside what we call solid lies a slow, intricate dance of atoms, a choreography so patient it hides from our senses. While clocks tick and seasons pass, materials remember, relax and evolve. Their time moves differently from ours, so slow it can feel eternal, yet always moving forward. Take glass, for example. It looks like a solid, it feels like a solid, but at the molecular level it's still in motion. Ordinary window glass is technically a frozen liquid, a substance caught mid-transition between flowing and rigid. When molten glass cools, its molecules never quite find a perfect repeating crystal arrangement. Instead, they freeze in place, trapped in disordered positions like dancers halted mid-performance. This arrested state is known as the glass transition. The molecules want to keep moving, to find a more stable arrangement, but the colder they get, the harder it becomes to shuffle. Their motion slows exponentially until it's imperceptible. That's why glass is often described as a supercooled liquid, though not because it's still flowing like syrup, that's a myth. A church window doesn't sag because the glass has dripped downward. It's thicker at the bottom simply because medieval artisans weren't perfectionists about uniform thickness. What's true, though, is that on geological timescales, glass would indeed creep ever so slightly toward equilibrium. It's just that the timescale is staggering. You could wait longer than the age of the universe and never notice the change. The glass would still be whispering its way toward order, one microscopic shuffle at a time. This kind of slow, hidden movement isn't unique to glass. Many materials carry their own private clocks, ticking in the language of atoms. Metals under stress can slowly deform through a process called creep. Over years, a bridge might sag by millimeters, or a turbine blade might stretch microscopically. The metal hasn't failed, it's just rearranging its internal structure atom by atom, adapting to the strain. The same goes for polymers, which gradually relax and settle as the tangled chains of molecules wriggle into slightly more comfortable configurations. Everything solid, when viewed through the long lens of time, is more like honey than stone. Even rocks age. Deep within Earth's crust, minerals realign, faults slide, and crystalline grains slowly grow. The mountains that seem frozen are in fact rising and eroding at the same time, keeping a balance that only makes sense when measured in millions of years. Matter may seem still, but time is always flowing through it, patiently sculpting its texture. Scientists studying these sluggish transformations talk about relaxation times, the characteristic pace at which a material responds to change. When you bend a piece of metal or cool a glass of molten silica, you disturb its internal equilibrium. The atoms, each one vibrating with energy, start to search for new configurations, but their search isn't smooth. They move through a complicated energy landscape filled with valleys and hills, some shallow, some deep. Finding a stable structure means descending into a deep valley, but getting there requires climbing out of shallower ones first. As the temperature drops or the stress eases, those atomic travelers move slower and slower, often getting stuck partway down. That's why some materials seem frozen yet remain technically restless. In these trapped states, materials can even develop a kind of memory. A piece of plastic that has been stretched remembers the shape it once held, snapping back when heated. Certain alloys, like nickel titanium, remember their original form even after being twisted, bending back into place when warmed. These are called shape memory materials, and their behaviour is a striking example of time encoded in matter. The atoms themselves store a record of their previous arrangement, locked into the energy landscape like a bookmark waiting to be reread. There's also a more poetic kind of memory found in aging glass and polymers. If you heat them slightly, cool them again, and then heat them once more, they can recall how long they've been left undisturbed. Their relaxation depends not only on their current temperature, but on their entire history, an echo of the conditions they've experienced. It's as though the material keeps a private diary written in atomic motions too slow for us to see. In recent years, physicists have discovered another, far stranger form of time hidden within matter: time crystals. Despite the name, they're not glittering gemstones that tick like clocks, nor do they violate the laws of physics. A time crystal is a special state of matter in which the system structure repeats, not in space like an ordinary crystal, but in time. The atoms or spins in a time crystal cycle between configurations in a steady rhythm, even without consuming energy or producing heat. They are not perpetual motion machines. Rather, they settle into a stable pattern of motion that repeats predictably, like a heartbeat that doesn't fade. Ordinary crystals break spatial symmetry. Their atoms arrange into repeating patterns that distinguish one location from another. Time crystals do something similar, but with temporal symmetry. They distinguish one moment from another, forming a rhythm that persists even when the external conditions remain constant. In practice, time crystals are created in carefully isolated systems. Quantum spins or ions manipulated by lasers and electromagnetic fields. They exist in laboratory conditions where interactions can be controlled and measured precisely. Though fragile, they show that even the laws of equilibrium can give way to more dynamic kinds of order. The discovery of time crystals has broadened our understanding of how matter organizes itself. It suggests that stability doesn't always mean stillness. A system can maintain perfect periodicity while remaining out of equilibrium, repeating its pattern forever without drifting toward chaos. It's a reminder that time, like space, can host its own architecture, structures that hum rather than stand. In a way, all materials carry echoes of this principle. From the slow rearrangement of glass to the regular vibration of atoms in a solid lattice, matter contains both static and rhythmic dimensions. The atoms in a crystal, though apparently frozen, vibrate around their positions billions of times per second. Those vibrations are the music of temperature, the atomic hum of existence itself. Cooling the crystal slows the tempo. Absolute zero would silence it completely, though no one has ever reached that perfect stillness. Even the most solid matter is full of motion, oscillations, drifts, and resonances that give it warmth and life. When we touch a surface, we're feeling the product of countless time-dependent processes balanced perfectly for the present moment. The glass beneath your fingertips has been aging since it solidified. The steel in a bridge remembers the heat of its forging. The wood in a table continues to expand and contract with humidity like a slow-breathing organism. Matter never forgets the time it has lived through. It's written into its structure at every scale. Time hides inside materials the way rhythm hides inside music. You can't see it, but you feel its influence everywhere. Each atom vibrates to a beat determined by its bonds, and the ensemble of those beats creates the familiar properties we rely on: strength, flexibility, transparency. The material world is not frozen. It's a slow-motion symphony, too vast and too patient for us to hear in real time. So even as we build monuments of stone and glass and call them timeless, the atoms inside are quietly evolving, adjusting, whispering to one another across the ages. Solids hum, liquids drift, and even the most inert objects carry memory in their microscopic motion. The world holds still only in appearance. Deep down, everything is keeping time. Every time you remember something, you change the universe a little. Not in a grand cosmic way. No new galaxies appear, no stars are born. But in a quieter, more personal sense. Neurons fire, molecules shift, and a trace of that moment becomes written into matter. But nature keeps an account of everything. Making a memory, storing data, even forming a thought, all come with a cost. To remember one thing, the universe must forget a little order. This connection between memory and entropy isn't just poetic, it's physics. In the mid-20th century, physicist Rolf Landau made a remarkable discovery that tied the abstract world of information to the concrete world of thermodynamics. He realized that erasing information isn't free. Every time a piece of information is destroyed, whether a computer overwrites a file or your brain lets go of a thought, some energy must be released as heat. This relationship, now known as Landau's principle, states that erasing a single bit of information, one yes or no, one or zero, requires at least a tiny amount of energy, proportional to the temperature of the system. That might sound trivial, but it's a profound link between knowledge and physics. It means information isn't some ghostly abstraction floating above reality. It is reality. Every bit you store, every note you write, every photograph on your phone has a physical presence. Information takes up space, requires energy to preserve, and generates entropy when changed or forgotten. Thinking, in the strictest thermodynamic sense, has a heat signature. If you've ever felt your computer warming under heavy use, you've experienced this law firsthand. The more data it processes, the more heat it releases, because erasing and rewriting memory is an entropic act. It's the same principle scaled up from atoms to circuits. In your brain, neurons fire and reset constantly, powered by chemical energy. Every time a pattern of activity shifts, a tiny fraction of energy dissipates as heat. The mind's thoughts are mirrored by the body's thermodynamics. In a way, this connection explains why the arrow of time feels so natural to us. Memory points forward. You can recall yesterday but not tomorrow because the universe, through entropy, only keeps reliable records in one direction. When an event occurs, it leaves imprints in light, sound, and matter that scatter outward, increasing entropy as they go. Those imprints make the event retrievable. If you see a footprint in sand, you know someone passed by earlier. The footprint exists because energy and order were exchanged when weight pressed into grains. To erase it, to smooth the sand perfectly flat again, requires work, effort, and more entropy. That's the essence of time's asymmetry. The past is filled with records because entropy has already done its work, scattering information across the environment. The future has no such records yet. It hasn't been written. The flow of time we feel, the difference between memory and anticipation, comes from this imbalance. The past leaves traces, the future does not. The concept of record-making runs deep in physics. When photons bounce off a table, they carry away information about the table's position and colour. When sound waves echo through a room, they encode the shapes that caused them. Every interaction leaves behind a little evidence, a trail of correlations written into the world. These records collectively form what we call reality. They are the stable scaffolding of the past. Without them, there would be no shared world. Only quantum ambiguity constantly shifting and unrecoverable. Information, then, is a measure of how much we can distinguish one state of the world from another. Entropy measures how many possibilities the world could take. The two are twins, joined by perspective. The more information you have, the less uncertain the world seems. The more entropy there is, the more uncertain it becomes. They move in opposite directions, but describe the same terrain, order seen from different angles. The link becomes even clearer when you look at the act of writing. A pen on paper transforms blank potential into a structured record, but the ink molecules that form each letter lose a bit of order as they spread and dry. The hand holding the pen burns energy. The air warms slightly around you. A perfectly blank sheet of paper is low in entropy, because its molecules are uniformly arranged. The written one, rich with information, has cost the environment a little disorder to exist. Every note, every sentence, every photograph represents a tiny trade-off between local order and universal chaos. In digital form, the same balance holds. A flash drive filled with data isn't energetically different from an empty one until you start erasing and rewriting it. Each change leaves a thermal echo, a whisper of energy lost to the background. If you could follow that trail of warmth, you could, in principle, reconstruct what was written. Information and entropy are never truly separate. They're two sides of the same coin, flipping endlessly in the universe's pocket. This dance between information and entropy may even be what makes life possible. Living systems are expert information processors. Cells copy DNA, repair errors, and respond to their environment by constantly writing and rewriting molecular records. To maintain that order, they must continually export entropy, releasing heat, consuming energy, keeping their internal records sharp while the surroundings grow slightly more disordered. Life doesn't escape the arrow of time, it rides it, using the flow of energy to stay briefly organized in an otherwise diffusive universe. Even memory itself, the most intimate form of information, depends on entropy's generosity. To remember is to build structure, to arrange neurons, molecules, or circuits into a pattern that mirrors something once experienced. That process takes energy and produces waste heat. Forgetting, paradoxically, costs energy too, because erasing a pattern means resetting the physical system that held it. The brain, like a library that burns calories to catalogue and reshelve its books, must constantly balance memory against metabolism. There's a quiet poetry to this. Every memory we create adds a little warmth to the world. Each photograph developed, each word typed, each neuron firing spreads a bit of entropy into the surroundings. The act of holding on to something, a face, a song, a moment, requires the universe to loosen its grip elsewhere. Nature remembers nothing for free. Seen this way, the arrow of time is not only about entropy spreading outward, but about information accumulating inward. The future grows more entropic, but the past grows richer in records. The more the universe changes, the more it remembers what it was. Our own lives mirror this process. We leave traces wherever we go, footprints, echoes, data, memories, and those traces form our personal history. The arrow of time moves forward because records only point one way. Landau's principle bridges the two realms, the digital and the physical, the mental and the mechanical. It tells us that memory is not just a metaphor, it's a thermodynamic reality. To remember is to rearrange matter. To erase is to release heat. The cost of knowledge is written in the temperature of the world. You could say that entropy is the price of story. Every narrative, whether told in ink, binary code, or biological memory, takes energy to write and leaves a signature behind. We move through life inscribing the universe with our choices, and the universe, ever generous, turns each act of order into a whisper of warmth. There are places in the universe where time itself begins to stretch, slow, and finally dissolve. Around a black hole, the steady rhythm of seconds and minutes loses all meaning. Clocks drift apart, moments elongate, and the very idea of now becomes slippery. It's not that time stops, it's that it bends so extremely that its flow depends entirely on where you are and how you fall. To understand why, imagine approaching a black hole, the collapsed remnant of a massive star, so dense that not even light can escape its gravity. Far from it, everything seems normal. Your clock ticks, your heartbeat matches its usual pace, and the universe around you feels unchanged. But as you draw closer, gravity's grip tightens not only on your body, but on time itself. Einstein's general relativity predicts that near such intense gravity, time slows down compared to regions farther away. The closer you approach the event horizon, the invisible boundary that marks the point of no return, the more stretched your seconds become. If you could hover safely near that boundary and look back toward the rest of the universe, you'd see time racing ahead. Distant stars would flicker and fade in fast motion. Meanwhile, someone watching you from far away would see the opposite. As you approach the event horizon, your movements appear to slow, your signals redshift into deeper and deeper hues, until eventually you seem frozen in place, forever hovering at the edge. This illusion is caused by the same gravitational redshift that stretches the light escaping from your surroundings. Every photon climbing out of that deep gravitational well loses energy, its wavelength lengthening as though time itself were being pulled apart. To the distant observer, your fall never completes. You fade away into darkness, frozen in a final moment that lasts for eternity. But for you, the traveller, nothing special happens at the horizon. You cross it without drama, and time continues normally along your personal path. It's one of relativity's most haunting lessons. Time does not have a single rhythm. Each observer carries their own clock, and near a black hole, those clocks diverge wildly. For you, falling inward, the trip to the centre takes only seconds or minutes. For the outside world, your descent never ends. A second at the edge of forever can stretch into infinity. Inside the horizon, the geometry of space-time twists in a way that defies intuition. In our everyday world, time and space are separate directions. One moves forward, the other outward. But inside a black hole, these roles trade places. Moving deeper inward is as inevitable as moving forward in time. There is no path that avoids the centre, no manoeuvre that lets you stop or turn around. The singularity at the heart of the black hole is not just a place, it's a moment that every infalling traveller must reach, as surely as any of us will reach tomorrow. What happens when you get there remains one of the great mysteries of physics. According to Einstein's equations, density and curvature become infinite, and the known laws of nature collapse. But quantum physics hints that there may be a more complete story, one where information isn't truly lost and singularities are replaced by something gentler, something we don't yet understand. Does time end inside a black hole, or does it merely change form? That question lingers at the boundary between what we know and what we can only imagine. Outside the horizon, however, the story continues. Black holes are not completely black. In the 1970s, Stephen Hawking showed that the edges of black holes emit a faint glow due to quantum effects, tiny pairs of particles forming near the event horizon, with one falling in and the other escaping. To distant observers, this appears as radiation slowly leaking from the black hole, carrying away mass and energy bit by bit. Over unimaginable timescales, this Hawking radiation causes the black hole to evaporate. The process is absurdly slow. A black hole the mass of our Sun would take roughly 10 to the power of 67 years to evaporate, a number so vast it dwarfs the current age of the universe, which is only about 13.8 billion years. The larger the black hole, the slower its decay. For supermassive black holes lurking in galactic centres, the timescale stretches into numbers that defy comprehension. In a universe that may one day grow cold and dark, those last evaporating black holes would be the final sparks of activity, a slow ticking at the very end of time's cosmic clock. From another point of view, though, time around a black hole is still just doing what it always does, following the geometry of space-time. The strange distortions we describe are not tricks but reflections of how gravity warps that geometry. The deeper you go, the more time itself curves toward the singularity. The idea of slowing down only makes sense when compared to someone far away. Locally, your watch still ticks 1 second per second. It's just that the meaning of second has changed relative to the rest of the universe. This relativity of time near black holes reveals something profound about reality. There's no single, universal timeline tying everything together. Instead, each observer traces their own path through space-time, and those paths can diverge so completely that communication becomes impossible. A black hole is the ultimate separation, not just of space, but of experience. Once you cross its horizon, your future becomes sealed off from the outside world's future. You and the universe part ways forever, each continuing your own story that the other can no longer read. And yet, black holes are not pure destroyers. They're also memory keepers. Their mass, spin and charge record the total information of everything that fell inside, even if the details seem scrambled. According to one view, that information may be preserved on the event horizon itself, encoded in a thin two-dimensional surface, a concept known as the holographic principle. If that's true, then black holes are cosmic archivists, holding their secrets in the stretched fabric of space-time, waiting for some future physicist, or perhaps nature itself, to decode them. The more we learn, the more black holes seem like laboratories, where time shows its most extreme behaviour. They blur the boundaries between beginning and end, between persistence and disappearance. Standing at their edge, the universe behaves like a mirror held up to its own limits. Time bends, light strains, and meaning seems to thin out. But through it all, the laws remain consistent. If you were brave, or reckless, enough to dive in, your own experience would end in a flash, but from the outside, you would appear eternal, frozen at the brink. Perhaps that paradox is what makes black holes so mesmerizing. They stretch not just matter, but understanding itself. They remind us that time is elastic, and that even its apparent limits may be part of a larger continuity we haven't yet fully grasped. In the deep future, when galaxies fade and stars burn out, the last flickers of Hawking radiation will mark the final pages of cosmic history. And in those final, fading sparks, the universe will still be keeping time, slowly, patiently, beautifully. Time has always been a story of change, of things cooling, expanding and settling into new forms. But what happens when change itself runs out? What does time look like when there's nothing left for it to do? The far future of the cosmos, stretched across unimaginable eons, offers an answer that's both eerie and peaceful. The universe is not ending in flame, but in silence. Right now, we live in an age of light. Stars still burn, galaxies still shimmer, and energy flows freely between the cold and the hot. Entropy, the measure of spreading energy, is always increasing, but there's still plenty of order left to dissolve. The difference between warm stars and cold space keeps the universe alive with activity. It's that contrast between bright and dark, motion and rest, that makes time feel like it's moving. But even this contrast won't last forever. Billions of years from now, star formation will slow. Galaxies will have used up their reservoirs of gas, and the great cosmic forges will grow quiet. The stars that remain will burn through their fuel and die one by one, massive ones collapsing into black holes, smaller ones fading into white dwarfs that cool into dark, cold embers. The night sky, once crowded with constellations, will thin. Planets will orbit dead suns. Galaxies will drift farther apart. The cosmos will grow dim, but time will keep moving forward. In roughly 100 trillion years, 100,000 times longer than the universe's current age, the last stars will flicker out. From then on, there will be no new starlight, no sunrise in any sky. The universe will enter its degenerate era, a vast cold span of existence where only remnants remain, black holes, neutron stars, and faint frozen embers of what once were suns. Energy will continue to spread out, but ever more slowly, as the remaining matter decays and cools. Even this dark age won't last forever. Black holes themselves, those eternal seeming monuments of gravity, will eventually evaporate through Hawking radiation. The smallest will vanish first, releasing faint bursts of energy, while the largest, those millions or billions of times more massive than the Sun, will take around 10 to the power of 100 years to dissolve. That's a 1 followed by 100 zeros, a timescale so vast it defies human imagination. Yet even those titanic spans are finite. In the end, every black hole will fade into the background, leaving only a thin, uniform mist of low-energy particles. This state is called heat death, though the name is a little misleading. It's not fiery or violent. It's the opposite. It's the quieting of all thermal gradients, the smoothing out of every remaining difference. When entropy reaches its maximum, energy becomes evenly distributed, and no process can extract work or create change. The universe doesn't collapse or explode, it just grows still. The temperature everywhere will hover near absolute zero, a few trillionths of a degree above nothingness. There will be no stars, no motion, and no time as we experience it, because nothing will happen to mark its passage. To some, this cosmic fate sounds bleak, a final exhaustion after so many ages of creation. But there's also a strange tranquility in it. The universe began in a burst of heat and noise, full of turbulence and fire. It ends in calm, its energy finally at rest. Everything that could happen has happened. Everything that could form has formed. What remains is a quiet, stable stillness, like the long exhale at the end of a song. Of course, physicists being physicists, they've imagined alternatives. Perhaps dark energy, the mysterious force accelerating the expansion of the universe, won't remain constant forever. If it strengthens over time, it could tear galaxies, stars, and even atoms apart in a scenario called the Big Rip. In that version of the story, space itself stretches so rapidly that all bonds, gravitational, atomic, molecular, are undone. Time would end not in stillness but in disassembly, as every structure in the cosmos unravels into nothingness. There's also the possibility of quantum decay, a sudden shift in the vacuum of space itself. According to some models, the vacuum we live in might not be the most stable configuration possible. A random quantum fluctuation could one day trigger a phase transition, creating a bubble of true vacuum that expands at nearly the speed of light, rewriting the laws of physics as it passes. It would be instant, total, and utterly unpredictable. No warning, no pain, just a quiet end written into the fabric of probability. Still, the most likely fate remains the slow fade. In this long twilight, even the meaning of distance will change. As the universe expands, the fabric of space will stretch so much that each remaining galaxy becomes isolated beyond reach, its light too redshifted to ever arrive. Eventually, only the faint glow of one's own galaxy will remain visible, until even that too drifts away beyond the observable horizon. Inhabitants of that distant future, if any still exist, would see an empty sky and conclude they were alone in the cosmos. The evidence of the Big Bang, the galaxies, the cosmic background radiation, all gone, erased by time's expansion. Entropy would still be increasing, but at a glacial pace. The universe's clock would be ticking slower and slower, not because time itself had stopped, but because so little would remain to measure it by. With no stars to burn, no heat to flow, and no processes to distinguish one moment from another, time would lose its practical meaning. The universe would persist, but it would no longer change. Some cosmologists call this the silent era. Others, more poetically, call it the dark eternity. In either case, the laws of physics would continue unbroken, even as the cosmos fell asleep. Quantum fluctuations might still shimmer faintly in the vacuum, tiny blips of energy popping in and out of existence, but they would be brief, random, and far apart. The universe would have become a vast, cold sea of near-perfect equilibrium, and yet, even in that equilibrium, there's an elegance to what remains. The ashes of stars, the dust of galaxies, the faint radiation filling space, all of it is a testament to what once was. The story of time would be written into the very temperature of the void, a record of all that the universe had ever done. The poet in us might find melancholy in such an ending, but the scientist can find beauty. The second law of thermodynamics isn't a curse, it's the ultimate act of balance. The universe began in fierce inequality, regions of unimaginable heat beside regions of perfect cold, a chaos of potential waiting to unfold. Over billions upon billions of years, it's been smoothing itself out, evening the scales, bringing every corner closer to equilibrium. Heat death isn't failure, it's completion. In that far future, there will be no more dawns, no more gravity wells, no more flowing rivers of energy. Just a quiet universe, stretched to the point where every fluctuation, every particle, every echo of light has finally spread as far as it can. Time will still exist as a coordinate in physics, but as far as experience goes, it will have no pulse. It's humbling to realize that everything, the stars, the atoms, even our own thoughts, is part of this slow unfolding. We are small eddies in the great current of entropy, brief arrangements of energy that borrow order for a little while. The universe is lending us its difference, letting us burn brightly before it evens out again. And when it does, when the last trace of motion softens into silence, perhaps it won't be an end so much as a rest. A cosmic pause after a performance, billions of years in the making. One day, the universe will exhale and simply forget to inhale again. Life has always been the universe's way of keeping time. Long before clocks or calendars, living things evolve their own rhythms, syncing themselves to the turning of the earth and the rising of the sun. Inside every creature, from the tiniest bacterium to the most introspective human, tick invisible oscillators made not of gears and pendulums but of chemistry and light. These are the biological clocks, quiet regulators that translate the physics of the cosmos into the pulse of living experience. Every cell in your body has some sense of time. Deep within the brain, a cluster of neurons called the suprachiasmatic nucleus acts as a kind of master clock, setting the rhythm for sleep, hunger, hormone release and alertness. It listens to the light coming through your eyes and adjusts accordingly, fine-tuning your 24-hour circadian cycle. But this isn't just a human quirk, it's a pattern written into life itself. Plants open their leaves and flowers at predictable hours. Coral reefs synchronize mass spawning events with lunar cycles. Even bacteria divide more efficiently when their internal biochemical clocks match the rhythm of day and night. At its core, biology's timekeeping is built on oscillations, chemical feedback loops that repeat with astonishing precision. Proteins build up, inhibit their own production, degrade, and then start over again. These cycles, though invisible, are as real as the swing of a pendulum. Temperature, light, and gravity all modulate their tempo, linking every heartbeat and every breath to the same cosmic rhythm that governs spinning planets and orbiting moons. But biology's relationship with time runs deeper than simple periodicity. Every organism experiences time differently, depending on its metabolism. For a hummingbird whose heart beats over 1,000 times per minute, the world moves in quick bursts. For a giant tortoise, whose heart may beat just a few dozen times an hour, the same world drifts by in slow motion. This isn't just poetic, it's measurable. The faster an animal's metabolism, the denser its sensory stream. A fly's brain, processing visual data at lightning speed, sees the world as a high frame rate movie, where your leisurely afternoon swat looks like a suspenseful slow-motion chase scene. To the fly, your hand is not quick, it's colossal and glacial. A fly experiences your afternoon like an action movie. Humans sit somewhere in the middle of this biological spectrum. Our sense of time flows neither as rapidly as a fly's nor as serenely as a tortoise's, but it isn't constant either. When we're children, summers seem endless. As adults, the same span slips by in a blink. Our subjective sense of time's passage isn't just mood. It's rooted in how memory and perception record experience. Psychologists have found that our perception of time depends on memory density, how many distinct moments we encode. When days are filled with novelty, attention and emotion, we store more detailed memories, and the interval feels long in retrospect. But when days are repetitive, when little changes from one to the next, our brain compresses them. Fewer memory markers mean shorter perceived duration. That's why childhood feels expansive and adulthood compressed. Novelty fades, and the mind's record of time thins. The clock outside hasn't changed, but the one inside has. Attention plays a role too. When you're fully absorbed in something, deep in a book, lost in a song, immersed in conversation, time seems to vanish. Hours slip by unnoticed because the brain's monitoring of duration quiets down while focus intensifies. Conversely, when you're waiting, bored, or anxious, time stretches. Each second gets examined, magnified, and elongated by awareness. The cliché is true, time flies when you're having fun, but only because your mind temporarily forgets to count. Memory itself adds another twist. Neuroscientists suggest that our sense of the present moment, the now we inhabit, isn't instantaneous but extended. The brain integrates sensory information over short windows, roughly a few seconds long, to create continuity. In that brief envelope, the world feels smooth and unbroken. Outside of it, the past dissolves into memory, and the future becomes anticipation. In a literal sense, we live a few seconds behind the universe, continuously updating a delayed broadcast of reality. On a larger scale, living organisms use time not just to survive but to anticipate. The migration of birds, the hibernation of bears, even the germination of seeds are acts of prediction, built upon ancient calibrations to light, temperature, and season. Life doesn't just endure time, it forecasts it. DNA itself carries echoes of past rhythms, the rise and fall of temperature cycles, the tilt of the planet, the pulse of geological ages. Every living system is a form of memory written into molecules, a record of adaptation that allows the future to be met with preparation rather than surprise. Yet our minds add a unique layer to this biological rhythm. Humans alone can think of time abstractly, past and future, cause and consequence, lifespan and legacy. We don't just experience time, we narrate it. We divide it into hours, days, and years, measure it, plan it, and sometimes mourn it. Our brains, evolved to track rhythms of light and dark, now track appointments, anniversaries, and cosmic calendars. The same neural machinery that helps birds time their migrations helps us remember birthdays and wonder about the fate of the universe. And still, for all our attempts to control it, time remains slippery. It flows differently under emotion. Joy collapses it, sorrow stretches it. Fear sharpens it, meditation blurs it. Moments of awe, watching a sunset, holding a newborn, standing beneath stars seem to slow everything down, as if the mind's clock pauses in reverence. Scientists suspect that such moments overwhelm our predictive models, forcing the brain to process each detail more slowly, creating the impression of expanded time. The physics hasn't changed, but perception has deepened. Even within a single lifetime, biology writes many rhythms. The fast oscillations of neurons firing merge into slower ones, the heartbeat, the circadian cycle, the aging process itself. Time at the cellular level moves differently than time at the conscious one, yet both follow the same arrow, the same general drift toward greater entropy and change. The skin renews, memories fade, bones calcify, and cells divide in sync with molecular clocks that have been ticking since life began. You are, in a sense, a collection of temporal instruments, some keeping seconds, others counting decades. This layering of timescales gives life its richness. The seasons turn, the heart beats, neurons spark, and within all of it, consciousness unfolds, an awareness suspended between physical time and psychological time. To physics, a second is a constant. To biology, it's flexible. To the mind, it's infinite and fleeting all at once. When we fall asleep, our inner clocks reset, hormones surge and temperature drops. Dreams unfold in compressed bursts where minutes can feel like hours or vice versa. In the morning, circadian genes stir awake, telling our cells that it's time to start again. It's the same 24 hours as always, but it never feels identical. Each day is a remix of the same fundamental rhythm, coloured by experience, mood, and meaning. All living things move to these overlapping tempos: heartbeats, breaths, sleep cycles, lifespans, and evolutionary scales, all nested within the wider tempo of cosmic time. From the microseconds of molecular reactions to the billions of years of planetary orbit, life is time made tangible. We sometimes imagine that physics dictates everything, but perhaps it only provides the metronome. The rhythm of existence beats steadily beneath us, but what we feel as time is our interpretation of that rhythm, the melody our consciousness writes upon it. Perhaps physics sets the tempo, but consciousness writes the melody. Humanity's oldest obsession might just be keeping time. From the shadows of sundials to the tick of pendulums and the pulse of quartz, each generation has tried to measure the moments more precisely than the last. But now our clocks have become so sensitive, so astonishingly refined, that they can feel the tug of gravity from a step up a staircase. We've entered an era where timekeeping brushes against the limits of physics itself, where each improvement not only sharpens our calendars, but rewrites what we know about the universe. For most of history, a second was a practical compromise. It began as 1/86,400th of a day, the division of the planet's rotation. Then came the age of atoms, when the world agreed to define the second not by Earth's spin, but by the steady oscillation of cesium-133 atoms, precisely 9,192,631,770 oscillations per second. It was a triumph of consistency, an unblinking rhythm written into nature itself. But even that atomic regularity, once unimaginable, is now being surpassed. Today's most advanced instruments, known as optical lattice clocks, measure time using light instead of microwaves. Instead of counting cesium's relatively slow oscillations, these clocks trap thousands of atoms, like strontium or ytterbium, in grids of laser light, where they vibrate hundreds of trillions of times per second. The higher frequency of light allows for far finer resolution, and the results are almost surreal. An optical lattice clock can maintain its accuracy to within a fraction of 10 to the power of -18. That's like losing or gaining a single second over the entire age of the universe. If you placed two such clocks side by side, they would agree so closely that their difference would only appear after billions of years of continuous ticking. The comparison between them is limited not by the clocks themselves, but by the imperfections of the laboratory around them. Tiny vibrations, stray magnetic fields, or even a passing truck outside. At this level of precision, gravity itself enters the conversation. Einstein's general relativity tells us that time flows more slowly in stronger gravitational fields, so much so that just standing on the floor instead of a chair makes you age infinitesimally slower. For most of human history, this difference was far too small to measure, but now these new clocks can detect the change in time flow between 2 points just a few centimeters apart in height. Raise one clock by the width of your hand, and it will start ticking measurably faster than the one below. The age-old expression, "time flies," is, it turns out, true. If you happen to be standing on a ladder, this gravitational sensitivity isn't just a curiosity. It opens a new era of chronometric geodesy, the science of mapping gravity using time. Instead of relying on satellites or weights, scientists can now measure how Earth's gravitational field varies simply by comparing ultra-precise clocks at different locations. A small difference in tick rate reveals how deep or shallow each clock sits in the planet's gravitational well. With networks of these clocks, we could one day monitor changes in sea level, ice melt, or underground water reserves with extraordinary accuracy, all by watching how time itself bends. The pursuit of ever more perfect clocks has also become a quiet probe of the universe's stability. If fundamental constants, like the speed of light or the fine structure constant, were to drift even slightly over cosmic timescales, these clocks would reveal it. By comparing optical clocks made from different atoms, strontium, ytterbium, aluminum, scientists can test whether the laws of physics remain truly immutable. So far, the universe appears remarkably consistent, but the very act of checking is profound. Our best measurement of time doubles as our best test of permanence. And as precision grows, so does imagination. Networks of optical clocks synchronized across continents, or even orbiting Earth, could serve as giant detectors of cosmic events. Passing gravitational waves, those ripples in space-time predicted by Einstein and first detected in 2015, subtly stretch and compress space itself. When a wave rolls through, it changes the distance between clocks ever so slightly, altering their rhythm. A global web of perfectly linked timekeepers could, in principle, pick up such waves directly through their tiny distortions of time. The same instruments that measure seconds might one day listen to the heartbeat of the cosmos. The implications ripple outward. GPS satellites already rely on precise timing to pinpoint locations on Earth, correcting for both their motion and weaker gravity in orbit. Without those relativistic adjustments, navigation systems would drift by kilometers each day. As clocks improve further, navigation could become astonishingly refined, capable of tracking motion down to millimeters, even across the oceans. The next generation of spacecraft could navigate the solar system not by radio signals, but by comparing time itself, using pulsars and atomic clocks as universal references. The growing precision also challenges the very definition of the second. The cesium-based standard, once untouchable, may soon be replaced. Scientists are preparing to redefine the second based on optical frequencies, anchoring it to the shimmering oscillations of light instead of microwaves. International committees are already comparing optical clock designs around the world, trying to determine which atom, which transition, and which technique should become humanity's next temporal foundation. When that change arrives, likely within the coming decade, it will mark a quiet but monumental moment. Time itself, as officially defined, will shift to a faster, finer beat. And yet, there's something almost philosophical about this pursuit. The more precisely we measure time, the more we realize that perfection isn't truly attainable. No clock, however refined, can exist apart from the universe that shapes it, the temperature, the gravity, the jitter of quantum noise. The deeper we chase certainty, the more the world reminds us that time is not just something to be counted, but something to be experienced. Even in laboratories filled with lasers, vacuum chambers, and cryogenic traps, time has a way of slipping past unnoticed. Scientists calibrate their instruments, compare frequencies, and write down digits that represent unimaginable stability. But outside the lab, the seasons still turn, the light still fades, and human lives still unfold in their own uneven tempo. Precision may refine our understanding, but it doesn't tame time. It only measures its texture more carefully. There's an almost poetic symmetry in where we've arrived. The same human impulse that once used shadows to track the day now uses photons to count the universe's heartbeat. The tools have changed, but the motivation hasn't. To understand change itself, to put order to the flow of moments, to feel connected to something continuous. Timekeeping is our way of staying synchronized with the cosmos, even as it races ahead. And as we continue refining these machines, chasing smaller uncertainties and deeper truths, it's worth remembering that time doesn't wait for us. Whether we measure it in seconds, oscillations, or cosmic ages, it flows according to its own laws, steady, indifferent, serene. Physics has carried us a long way in understanding time. From ticking atoms to bending space-time, from quantum uncertainty to cosmic stillness, we've learned to describe the mechanisms behind change with extraordinary precision. We can measure how time dilates near black holes, how entropy gives it direction, and how particles may dance through it in superpositions of order and sequence. Yet, for all that clarity, something remains just out of reach. The feeling of time. Physics can describe the scaffolding of moments, but not the experience of moving through them. To a physicist, time is a coordinate, a dimension interwoven with space, forming the fabric through which events unfold. Equations chart its passage, constants shape its curvature, and clocks quantify its rhythm. But the tick of a clock isn't the same as the sense of a moment. Between the mathematics and the melody lies the most human of mysteries, why time feels alive. This is where physics and philosophy part ways, not in opposition, but in complement. Physics tells us what time does. It cannot tell us what time is. The laws describe relationships between things, how one event follows another, how energy changes form, how the universe expands and cools. They describe structure, not significance. Meaning is the province of the mind, the part of reality that measures not with rulers and equations, but with memory, anticipation, and wonder. We can calculate the half-life of uranium, or the lifespan of stars, but we cannot plot on a graph what it feels like to watch a loved one age, or to hear the final note of a song fade into silence. Those moments are made of neurons and physics, yes, but their essence lies elsewhere, in perception, emotion, consciousness. Physics gives us the score, but the music happens in our listening. It's tempting to believe that if we refine our equations enough, the mystery will disappear. But every time science advances, it seems to reveal not an answer, but a deeper landscape of questions. Einstein turned time into a flexible dimension. Quantum mechanics fractured it into probabilities. Cosmology stretched it across eternity. None of these discoveries removed the wonder. They only changed its shape. Our models of time are maps, not the territory. They're extraordinarily accurate representations of how the universe behaves, but no map can make the terrain disappear. The second law of thermodynamics, for instance, explains why entropy grows and why the arrow of time points forward. But it doesn't tell us why we feel the forwardness. It tells us why broken eggs don't unbreak, but not why the sight of an unbroken dawn stirs something wordless within us. Relativity too redefined our sense of simultaneity, showing that now depends on where and how you move. Yet even as Einstein dismantled the universal present, we still live in one, our own, fleeting continuous now. The physics is real, but so is the experience. The two are not in conflict. They're simply different descriptions of the same unfolding. Quantum physics takes that humility even further. At its deepest level, time may not flow at all. Equations like the Wheeler-DeWitt formulation describe a universe that is static, timeless, complete. Change emerges only when parts of it compare themselves to others. If that's true, then perhaps our sense of movement through time is not an illusion but a relationship, a kind of cosmic conversation between patterns. We experience it not because time exists separately, but because we are embedded within it, made of it, shaped by its correlations. Still, even if we understood every mathematical contour of this timeless whole, something essential would remain unmeasured. The feeling of passing through moments, of living a life that unfolds one instant at a time, belongs to experience, not to theory. It's the difference between knowing the chemistry of water and knowing what it feels like to float. Physics excels at humility. It doesn't claim to have all the answers, only the most reliable ones it can test. It reminds us that reality is bigger than our perspective, and that even our finest instruments are tuned to a limited band of the cosmic symphony. The universe may not check its watch, but it keeps excellent attendance. The closer we look, the more we find that time resists simplification. It is both absolute and relative, continuous and discrete, personal and universal. It's the stage and the performance, the frame and the film. Physics can show us the patterns but not the poetry. And maybe that's the point. Perhaps time's greatest gift is that it allows both to coexist, the measurable and the meaningful, the external and the internal. Entropy gives it an arrow, relativity gives it flexibility, quantum mechanics gives it texture, and consciousness gives it colour. Each perspective adds something essential, yet none can claim to own the whole picture. When we watch the sunset, we're seeing the universe in motion, light stretched by space, photons scattered through air. But we're also witnessing a rhythm that speaks directly to the heart, a pattern older than species, encoded in biology and culture alike. The physical explanation doesn't diminish the beauty, it deepens it. To understand why the sky glows is not to rob it of wonder. It's to realise that wonder itself is part of what time creates. It's easy to imagine time as an adversary, something that takes away, erodes, and ends. But in truth, it's what allows anything to exist at all. Without time, there would be no change, no memory, no music or movement or growth. Even rest, even stillness, is a part of time's offering. To live in time is to share in the universe's unfolding, to be a brief but genuine part of its rhythm. The physicist's view and the poet's view are not so different. Both seek to describe motion, one in equations, the other in language. Both rely on patterns. Both chase meaning across the same fleeting seconds. The universe may not care about human notions of past and future, but through us, it gets to feel them. In our awareness, time becomes conscious of itself. And so, as we reach the end of this long exploration, perhaps the best thing to take from physics is its humility. Its laws are true within their scope, but they never pretend to be the whole story. The experience of time, its warmth, its melancholy, its momentum, belongs to a domain that no formula can fully capture. Time, after all, is what allows everything else to happen. Galaxies to spin, atoms to vibrate, minds to remember, and hearts to rest. It carries the universe forward, but it also carries us inward, to reflection, to appreciation, to stillness. The story of time isn't about what ends, it's about what unfolds. It's about the delicate rhythm of being, the slow grace of existence, and the quiet reminder that every second is a small miracle of continuity. Time, for all its complexity, ends where it began, with a single steady rhythm. From the flicker of atoms to the turn of galaxies, from your own heartbeat to the ticking of clocks in quiet laboratories, everything that exists moves to time's invisible beat. It defines all change, yet it never changes itself. No matter how far physics has taken us, through relativity, entropy, and the deep stillness of quantum space, we keep returning to that same quiet paradox. Time is motion, and motion is the language of being. We've followed that rhythm across scales vast and small, from seconds to aeons. We've watched it stretch beside black holes, slip between particles, and dissolve into the heat death of the cosmos. And through it all, it has remained a constant companion, patient and unhurried. Even in the silence between beats, it persists, steady as breath, vast as thought. In the beginning, time was counted in shadows, then in pendulums, in gears, in quartz vibrations, and now in the trembling light of atoms. We've built clocks that can feel gravity's pull, clocks so precise they can tell you the time difference between the floor and the ceiling. And yet, for all our effort to measure it, time continues to move on without us, perfectly indifferent. The universe doesn't need a clock to keep its schedule, it simply does. We've seen how time bends and stretches under gravity, how it can slow for one observer and race ahead for another. We've glimpsed the arrow drawn by entropy, forever pointing forward, even as the universe grows quieter with every passing century. We've imagined the far future when stars fade and even black holes exhale their last sighs of radiation into the cold. But we've also seen how in the smallest corners of existence time pulses with life, through circadian rhythms, through memory, through consciousness itself. Every living thing is a clock, beating out its own measure of the universe. In a way, we're all made of time. Each cell carries it, each breath marks it, and each thought stretches it into meaning. The seconds we experience are shaped by memory, emotion, and perception. A moment of wonder feels eternal. An hour of waiting lasts forever. A year in reflection vanishes in a blink. Time does not flow the same for everyone because we don't just move through it. We make it in how we feel and remember and change. Physics can tell us what time does, but not what it feels like. The laws are silent on the part that matters most, the part that lives inside us. The tick of an atomic clock is real, but so is the way a song seems to suspend time, or how a quiet evening can stretch endlessly before sleep. Between those two kinds of knowing, the mathematical and the emotional, lies the full experience of existence. Somewhere in that meeting point between cosmic precision and human perception is where time becomes beautiful. It's where entropy meets meaning, where the cold elegance of the universe touches the warmth of awareness. It's where we remember that even as everything changes, something constant remains, the continuity that holds it all together. When physicists look outward, they find time expanding with space. When philosophers look inward, they find time expanding with thought. But it's really the same discovery, seen from two sides. The world outside and the one within both unfold in rhythm, both tracing arcs of becoming. Time is not separate from us. It is the form our existence takes. And so, as we close this long journey through billions of years of ideas in a single night, perhaps the lesson is not to master time but to make peace with it. To see it not as a force that takes, but as the quiet background that allows everything to happen, every orbit, every dream, every heartbeat, every still moment between them. The universe began with motion, and it will end in stillness. But perhaps stillness is only motion so smooth we no longer feel it, a kind of cosmic rest between notes. The clock never really stops, it just becomes silent enough to hear the music it's been keeping all along. May every passing second remind you that stillness is also motion, quietly disguised. Good night, and may your next hours pass gently.